Hello fellow sapiens, and welcome to Sleepless Homo. Before we begin, take a moment to slow your thoughts, quiet the mind, and let this story move at its own pace. Whether you're easing towards sleep, unwinding after a long day, or simply keeping yourself company while cooking, showering, or working with headphones, this channel is here for you. Sleepless Homo is soft science, not wild speculation. Humble, careful storytelling that doesn't always have the answers, but does its best to share what we know so far. If you value this kind of long-form, educational calm, I invite you to like and subscribe. It helps this content reach more people, and together knowledge can outlast noise. I'd love to hear in the comments, do you use these videos to drift into sleep or to focus while doing other tasks? Or tell me, what time of day and place do you usually join us from? And if you do drift off during some chapters, I've added timestamps in the description so you can return the next day. The full story is always worth it. And as always, stay curious, stay calm. Now, let's step back 1 million years to the last days of Paranthropus and the first real humans. Let us step back before the clock struck 1 million years ago, when the world of our ancestors was already being shaped by forces they could not see, but that we are only now beginning to understand. What kind of world did they inherit on the cusp of that great turning point we call the mid-Pleistocene transition? The time we are entering lies between 2 million and 1.8 million years ago, an interval both strange and familiar. Strange, because the continents were already where they are now, and yet the animals walking those lands were unlike anything we share the planet with today. Familiar, because the rhythms of the Earth, the advancing and retreating of ice, the slow turning of climate, were beginning to echo the same cycles that still govern our survival. This was the age when our lineage, the genus Homo, was no longer a quiet newcomer. Homo erectus had spread across Africa and was already peering into Asia, carrying with them stone tools that were unlike anything earlier hominins had crafted. And yet, they were not alone. Paranthropus boisei, a close cousin with jaws built like an anvil, still thrived in the eastern African Rift Valley, a reminder that the human story was never singular, but crowded with possibilities. To picture this world, one must imagine Africa not as a static backdrop, but as a land locked in ecological negotiation. The Rift Valley was widening, mountains rose, lakes swelled and shrank. Grasses of the C4 variety expanded across savannas, filling the air with the scent of dry season resilience. Herds of grazing ungulates, from early zebras to antelopes whose descendants we no longer know, moved across these plains in restless waves. With them came predators, saber-toothed cats, hyenas of enormous size, and lions that were already formidable, but not yet the rulers we know. In this web of life, hominins did not dominate. They were participants, vulnerable, yet increasingly resourceful. The hook here lies in asking, if Homo erectus was so adaptive, why did other hominins such as Paranthropus endure alongside them? The answer lies in dietary partitioning, a concept ecologists still use today. Paranthropus boisei had massive molars and strong chewing muscles, adapted for processing tough plant matter. Stable isotope studies of their tooth enamel suggest that they were specialists in consuming C4 plants like grasses and sedges. Homo erectus, by contrast, was not locked into one niche. Their dental morphology shows a more generalist approach, and their archaeological record, stone tools associated with cut-marked bones, confirms a flexibility that included both plants and meat. In this way, the Rift Valley around 2 million years ago resembled a crowded cafeteria, each hominin lineage taking a different dish, minimizing direct conflict while maximizing survival opportunities. But it was not only diet that defined this prelude. Around 2 million years ago, the technological tradition we call the Acheulean was emerging. At sites such as 𝐓𝐈𝐌𝐿𝐄𝐒 in Kenya and Konso in Ethiopia, large bifacial tools, crude handaxes and picks, appear in the record. Their presence alongside more ancient Oldowan flakes suggests that hominins were experimenting, layering new strategies on top of old. The earliest Acheulean tools are not refined or symmetrical, but they represent a shift in cognition. Striking a large flake from a giant core required planning, force and precision. Shaping that flake into a cutting edge showed an ability to impose form onto stone, to imagine a tool before it existed. These were not abstract works of art, but functional necessities for butchering carcasses, processing wood, and perhaps digging. And though we know this innovation was revolutionary, it did not immediately sweep aside other traditions. The Acheulean began as one thread in a tangle of approaches to survival. At Juma's Korongo in 𝐓𝐈𝐌𝐿𝐄𝐒𝐏 Gorge, in levels we now date to around 1.5 to 1.3 million years ago, the bones of hippos, giraffes, and large bovids bear the marks of stone tools. Percussion scars, cut marks, and the pattern of butchery show that Homo erectus had access to meat, sometimes before carnivores, sometimes after. But the roots of this practice stretch back into the interval just before 1 million years, when the techniques of carcass processing were already well established. Homo erectus was not simply a scavenger trailing behind lions. Evidence from Bed 2 of Olduvai and from Kubifora in Kenya indicates that they often reached carcasses first, stripping meat from bones and breaking them for marrow. The distinction between hunting and scavenging may not have mattered as much as we imagine. What mattered was access, timing, and coordination. While Homo was expanding in range and technology, Paranthropus seemed to hold steady. For nearly 1 million years, 𝐓𝐈𝐌𝐄𝐒𝐓𝐀𝐌𝐏𝐒 exhibited remarkable morphological stasis. Their skulls and jaws remained consistent, their dietary adaptations stable. This endurance has been described as evolutionary durability, a testament to how well-specialized traits can serve a lineage for long spans of time. Yet stability can be a double-edged sword, and though we will explore their eventual decline later, at this moment in history they were still thriving. Their fossils remain abundant in the Turkana Basin, in the Awash Valley, and in Olduvai, suggesting that their ecological strategy was working, for now. The climate of this era adds another layer to the story. Between 2 million and 1.8 million years ago, the Earth's glacial rhythms were still governed by cycles of 41,000 years, tied to the tilt of the planet's axis. These oscillations produced alternating wet and dry periods across Africa. During wetter phases, deep lakes filled the rift depressions, vegetation flourished, and hominin populations may have expanded. During drier intervals, lakes shrank or vanished, woodlands retreated, and grasslands dominated. Hominins had to move, adapt, or perish. This environmental variability has been called the variability selection hypothesis by paleoanthropologists such as Rick Potts, and it posits that it was not stability but unpredictability that shaped our lineage. Flexibility became an evolutionary advantage, favouring those who could adjust diets, technologies, and ranges quickly. So, what did the world just before 1 million years look like in its broader geography? Beyond Africa, Homo erectus had already reached Western Asia by 1.8 million years ago, as the famous site of Dmanisi in Georgia reveals. Here, skulls of small-bodied hominins with a mix of primitive and advanced traits tell us that Homo erectus was not a single, uniform form. They carried older one-like tools, not yet Acheulean handaxes, suggesting that technological expansion lagged behind biological dispersal. To the east, evidence from Java hints at an even earlier arrival, though the dating remains debated. What matters is that by this time, our genus was not confined to Africa. It was a lineage testing the edges of continents, learning to survive in forests, savannas, and temperate plains. Meanwhile, the other large primates of Africa provide a backdrop to the human story. 𝐓𝐈𝐿𝐼𝐿𝐼 oswaldi, a giant baboon species, also adopted a C4-dominated diet. Their enamel isotopes show a convergence with Paranthropus, suggesting overlapping niches. Unlike Paranthropus, 𝐓𝐈𝐿𝐼 survived longer, though eventually they too would vanish. The ecological dance among hominins, primates, and herbivores reveals that competition was not only between humans and animals, but among cousins within the primate order. If we step back and see this world as a whole, it is neither a triumphal march toward us nor a tragedy of lost lineages. It is a branching thicket of experiments. Homo erectus, with their tools and wider range, represented one path. Paranthropus, with their specialization, embodied another. Australopithecus species had largely faded by this time, but their legacy persisted in both lineages. The landscape itself was an active participant, reshaping opportunities and closing others. Rivers shifted. Volcanic eruptions deposited tuffs that now allow us to date these events, and tectonics sculpted basins where fossils could be buried and preserved. The haunting question we must close with is this: what did it feel like to be there, in that interval just before 1 million years? To walk as Homo erectus, armed with a crude hand axe, watching the horizon for predators. To live as Paranthropus, grinding through tough grasses with jaws honed by evolution, unaware that the world was about to change. We cannot know their thoughts, but we can trace their bones, their tools, their isotopic signatures, and the sediments that entomb them. What we find is a world on the edge of transition. The players were on stage, the climate was shifting its rhythm, and the story of humanity was about to pass through a narrowing gate. That is the world our ancestors inherited before the clock struck 1 million years. Why evolve jaws that could crack nuts when nuts were not even the main meal? That is the puzzle of Paranthropus 𝐓𝐌𝐿𝐄𝐒𝐌𝐏𝐒, a hominin who has earned nicknames like the Nutcracker Man, even though modern analysis shows that nuts and hard seeds were likely not their staple food at all. Between 2.3 and 1.3 million years ago, in the shifting landscapes of eastern Africa, Paranthropus walked upright, bore the unmistakable stamp of being human-like, and yet was adapted to eat in a way that no human alive today can quite imagine. Their bones and teeth, preserved in sites across the Rift Valley, whisper a paradox. They looked like they were built to crush, but chemically they lived on something softer, stranger, and perhaps far less appealing to us. The reveal begins with their anatomy. A typical Paranthropus 𝐓𝐌𝐿𝐄𝐒𝐌𝐏𝐒 skull is a work of evolutionary architecture. The cranium is wide with flaring cheekbones that create broad faces. The jaws are massive, built like structural beams, supporting molars and premolars so large that they dwarf those of any other hominin. In some specimens, individual molars exceed 2 centimeters across, teeth the size of bottle caps. These grinding surfaces are thickly enameled, capable of absorbing intense pressure. Rising from the top of many male skulls is a sagittal crest, a ridge of bone to which the temporalis muscle anchored. This is the same feature seen in modern gorillas, evidence of powerful chewing muscles. Taken together, the skull of Paranthropus looks designed for one thing above all: chewing tough fibrous material for long stretches of time. Early anthropologists, when they first examined these fossils in the mid-20th century, concluded that Paranthropus must have lived on a diet of nuts and hard seeds, hence the famous nickname Nutcracker Man. But the scientific process is iterative, and over the last decades new methods have shifted our view dramatically. Microwear analysis, which studies the microscopic scratches and pits on the surfaces of teeth, suggests that Paranthropus teeth were not covered in the patterns typical of seed-eaters. Instead of showing heavy pitting like a seed-crushing monkey, their teeth show wear more like grazers or grass-eating animals. This was puzzling, because grass is not the kind of food we expect hominins to target directly. The paradox deepened with isotopic studies. By examining the ratios of carbon isotopes in the enamel of fossilized teeth, scientists can determine whether an animal consumed primarily C3 plants, trees, shrubs, and fruits, or C4 plants, tropical grasses and sedges. The signal from Paranthropus 𝐓𝐌𝐿𝐄𝐒𝐌𝐏𝐒 is unequivocal. More than 70% of their diet came from C4 sources. This is astonishing, because few primates alive today specialize so heavily in C4 plants. Our closest relatives, chimpanzees and gorillas, are overwhelmingly C3 feeders. The closest analogy to Paranthropus is not another primate, but grazing antelopes and baboons like Therapithecus, whose teeth also bear the isotopic mark of grass consumption. This raises an almost comical image. A hominin who looked like us in posture, who walked upright and used tools at least occasionally, but whose diet was chemically indistinguishable from that of a zebra. And yet here, the information becomes murkier. Stable isotope studies tell us the source of carbon, but they cannot specify which parts of the plant were consumed. Did Paranthropus spend their days chewing blades of grass? This seems unlikely, as human teeth and guts are poorly suited to digesting raw grass leaves. A more plausible scenario is that they targeted underground storage organs, roots, tubers, rhizomes, that belong to C4 plants. These starchy, fibrous tissues would have been difficult to access without strong jaws and teeth, but once processed they provided energy-rich calories. Another possibility is that they targeted the seeds of sedges and grasses, or soft young shoots available seasonally. The truth may lie in a flexible combination. a general pattern of tough, fibrous fallback food supplemented with whatever was available. The strength of their chewing apparatus suggests that Paranthropus was adapted to survive the worst times, when preferred foods like fruits were scarce. In such seasons, fallback foods become central to survival. The paradox is that adaptations for fallback foods can dominate anatomy, even if those foods were not the most desirable. A creature may evolve jaws capable of cracking the hardest tubers because those tubers are what keep it alive during droughts, even if it prefers softer fare when conditions allow. This concept helps explain why the isotopic signals look extreme, while the microwear suggests more variation. Day to day, Paranthropus may have enjoyed a diverse diet, but over the span of a lifetime, the chemical record shows that the bulk of their calories traced back to C4 resources. Their postcranial skeletons, though rare, confirm that Paranthropus walked upright like other hominins. The partial skeleton 𝐓𝐻80, discovered in Olduvai Gorge, includes limb bones suggesting a body built for terrestrial life. They were not knuckle walkers, not climbers of the canopy, but walkers of open landscapes. Their habitats stretched across eastern Africa, from Ethiopia to Tanzania to Malawi, wherever grassland and wetland mosaics provided the plants they relied upon. For nearly 1 million years they endured, holding on to their niche. One striking fact about Paranthropus is their evolutionary conservatism. While Homo erectus brain cases expanded and tools became more elaborate, Paranthropus skulls remained remarkably similar over hundreds of thousands of years. Their chewing adaptations, once established, did not change much. This suggests a stable ecological strategy, one that was effective as long as the environment maintained broad swathes of grassy habitat. But it also means they lacked the plasticity that Homo seemed to possess. Paranthropus doubled down on a single survival tactic: process tough, fibrous food better than anyone else. It is important to be humble here. We cannot directly observe what Paranthropus ate. We do not have preserved meals or stomach contents. All we have are teeth, bones, isotopic traces and wear patterns. These clues are enough to frame hypotheses, but they leave space for error. Perhaps Paranthropus consumed more meat than we think, scavenging opportunistically. Some sites do associate Paranthropus fossils with stone tools, though whether they made or merely used them is debated. The simplest interpretation is that they were primarily herbivorous specialists, but not necessarily strict vegetarians. Like modern gorillas, who occasionally eat insects or small animals, Paranthropus may have supplemented a plant-heavy diet with occasional animal protein. Still, the heart of the mystery lies in their paradoxical adaptations. Why evolve the ability to crush the hardest foods, yet mostly eat softer ones? The answer may lie in resilience. Evolution favours traits that preserve survival under stress, not traits that maximize pleasure during abundance. Paranthropus' massive jaws were insurance policies. When drought shriveled fruits and leaves, when competition limited access to high-quality resources, their fallback foods kept them alive. They were, in a sense, survivalists of the Pleistocene, adapted not for the best of times, but for the worst. As we examine these fossils today, the haunting question is whether specialization was both their triumph and their eventual undoing. They lived successfully for over 1 million years, longer than our own species has yet existed. Their strategy worked, until conditions changed beyond their ability to adapt. But at the moment we are considering, between 2.3 and 1.3 million years ago, they were not a lineage in decline. They were flourishing, spread widely, and leaving behind fossils that remain abundant compared to early Homo of the same time. The paradox of their diet makes them fascinating, but we must resist the temptation to see them only in hindsight. To their contemporaries, Paranthropus was not a doomed experiment, but a thriving presence on the landscape. As a final reflection, we might ask, what would it have felt like to encounter one? Imagine an upright figure, perhaps a little shorter than you, broad-faced with massive jaws, chewing slowly on a stalk of sedge near a lakeshore. They are recognisably human-like in gait, yet their expression and anatomy mark them as something apart. They are both kin and other. Their success lay not in abstract thought or in elaborate tools, but in their ability to turn the unpalatable into sustenance. They remind us that humanity's story is not only about intellect and invention, but also about the many ways bodies can be shaped to endure. Their teeth, worn down by years of grinding, still carry the echo of meals taken under African skies more than 1 million years ago. How can a grassland specialist go extinct in a grassland world? That question has haunted paleoanthropology ever since Paranthropus boisei disappeared from the fossil record around 1 million years ago. Their skulls and teeth looked so perfectly designed for a life spent grazing on C4 vegetation that their extinction seems almost illogical at first glance. After all, grasslands were widespread across eastern Africa during the lower Pleistocene. If anything, they appear to have been expanding during key intervals. But here is where deeper geological and ecological evidence complicates the picture. The survival of a species is not determined by broad categories like grassland present or grassland absent. It is shaped by subtle shifts in climate, atmospheric chemistry, plant physiology, and competition with other herbivores. When scientists began to combine fossil evidence with geochemical proxies, they discovered that the story of Paranthropus' disappearance is tied to ghost grasslands, vanishing menus, and a world in the midst of profound climatic change. To understand the paradox, we must begin with the role of C4 grasses themselves. These grasses use a photosynthetic pathway that allows them to thrive under conditions of low atmospheric carbon dioxide and high temperature. They are dominant across the tropics today, and during the Pleistocene they expanded widely across eastern Africa. Paranthropus boisei, as stable isotope analysis shows, relied heavily on these grasses and their underground storage organs. But the key point is not just the presence of grass, but the stability of grassland ecosystems. Between 1.4 and 1 million years ago, the Earth entered a climatic reorganization known as the mid-Pleistocene transition. Glacial cycles lengthened from 41,000 years to roughly 100,000 years, producing greater extremes of wet and dry conditions. The atmosphere also experienced fluctuations in carbon dioxide. Reconstruction suggests that PCO2 levels were lower and more unstable during this interval, a critical factor for plant growth. When carbon dioxide dropped, even C4 grasses became more stressed, producing less biomass. Woody vegetation could pulse forward during wetter phases, altering the structure of habitats in ways that undermined the niches of grazing specialists. The Quinn and Lepre study of 2021 highlights how these processes unfolded in the very landscapes Paranthropus once roamed. By examining soil carbon isotopes from multiple horizons in the Kubifora Formation of Kenya, they tracked long-term vegetation changes across the crucial interval of 1.4 to 1.0 million years ago. What they found was not a simple story of monotonous grassland, but of contraction and instability. Grasslands that had once been dominant shrank, replaced episodically by woody cover. The isotopic data suggests that C4 biomass decreased, reducing the available food for grazers. This was not a permanent collapse, but rather a pulsing pattern of expansion and contraction, a flickering between grassy and woody states. For a specialist like Paranthropus boisei, such instability was devastating. Their diet was so tightly bound to C4 resources that the reduction of those resources meant narrower options, nutritional stress, and ultimately population decline. Adding to this ecological squeeze was the rise of ruminant herbivores. Bovids, with their complex stomachs and efficient digestive systems, are uniquely adapted to extracting energy from fibrous grasses. During the lower Pleistocene, bovids diversified and increased in abundance. Quinn and Lepre note that as C4 grasslands contracted, the competition among grazers intensified. Paranthropus, with its powerful jaws but simple gut, was no match for bovids in terms of efficiency. While they could chew through tough food, their digestion did not match the efficiency of ruminant fermentation. This meant that when grass became limited, bovids had the edge, outcompeting Paranthropus for the same resource base. Fossil assemblages from sites like Kubifora show an increasing prevalence of grazing ungulates precisely during the time that Paranthropus fossils vanish. Another layer of complexity comes from the interaction between volcanic activity, tectonics, and ecosystems in the Rift Valley. Sedimentary sequences reveal repeated cycles of lake expansion and contraction. These lakes acted as ecological anchors, providing fresh water and stabilizing vegetation during dry phases. But around 1.2 to 1 million years ago, evidence from lake cores indicates heightened variability. Large freshwater bodies became more ephemeral, wetlands dried more frequently, and woodland patches expanded. For Paranthropus, who likely depended on habitats near lakeshores and wetlands where sedges and grasses were abundant. This meant the steady shrinking of prime foraging grounds. Ghost grasslands remained on the landscape, but they were no longer as predictable or as nourishing. One might ask, why did this affect Paranthropus more than other primates? After all, baboons, monkeys, and even early Homo survived these fluctuations. The answer lies in specialization. Paranthropus boisei had committed to a narrow diet, reflected in their anatomy. Their skulls were not versatile chewing machines but tailored grinders. They lacked the behavioural and technological flexibility of Homo erectus, who could supplement plant foods with meat, marrow, and diverse foraging strategies. But in this narrative, we're not yet introducing direct Homo Paranthropus competition. Instead, the emphasis is on how environmental instability and herbivore competition reshaped the landscape of survival. The atmospheric story is equally compelling. Reconstructions of carbon dioxide levels from marine sediment cores show that the interval between 1.4 and 1 million years ago included some of the lowest concentrations of PCO2 in the last several million years. Levels may have dropped below 200 parts per million at glacial peaks. At such low concentrations, plant growth is suppressed. Even C4 grasses, which are more tolerant of low CO2 than C3 plants, cannot maintain high productivity under these conditions. The result would have been grasslands that looked healthy from a distance but provided fewer calories per bite. This phenomenon, invisible in the fossil record except through chemical proxies, may explain why Paranthropus faced nutritional bottlenecks despite grasslands remaining on the landscape. We can illustrate this paradox with a thought experiment. Imagine standing on the shore of an ancient lake in the Turkana Basin 1,100,000 years ago. You see grassy plains stretching to the horizon, dotted with grazing antelope and zebras. It looks like a world built for Paranthropus. But the grasses are not the same as those that flourished a few 100,000 years earlier. Their growth is stunted, their biomass reduced. Bovids graze efficiently, extracting energy through microbial fermentation in their stomachs. Paranthropus, with its massive jaws, can chew the blades down, but the energy yield is insufficient to sustain large populations. What appears to be an abundant grassland is, in fact, a ghost grassland, visually present but nutritionally impoverished. As scientists, we must acknowledge that this reconstruction is tentative. We do not have direct records of Paranthropus' diet in this final phase. The isotope data provide population-level trends, not individual meals. The ecological context is reconstructed from soil isotopes, pollen grains, and faunal assemblages, each with its own limitations. Still, the convergence of evidence points to an ecosystem becoming less hospitable to C4 specialists. The disappearance of Paranthropus from the fossil record by about 1 million years ago is consistent with these pressures. It is a reminder that extinction is not always caused by dramatic cataclysms, but by slow ecological attrition, the narrowing of options until survival becomes impossible. The haunting question that remains is this: how does a lineage endure for nearly 1 million years and then slip quietly away, leaving behind only jaws and teeth in the sediments? Paranthropus boisei was not a failure in evolutionary terms. It thrived longer than our own species as yet existed. Its adaptations were perfectly suited to a world that, for most of its span, provided stable C4 resources. But when that world became unstable, when carbon dioxide fell, when woody plants surged into grasslands, and when ruminants claimed the same niche more efficiently, the strategy of heavy chewing became a trap. They became prisoners of their own success, bound to a diet that no longer delivered what it once had. Their extinction is less a story of sudden doom than of a menu that vanished, a quiet erasure of opportunity in a world that looked deceptively familiar. What does one shattered skeleton in 𝐓𝐈𝐌𝐿𝐿 tell us about a whole vanished lineage? In the year 1959, Mary Leakey's discovery of a Paranthropus boisei skull at 𝐓𝐈𝐌𝐿𝐿 Gorge set the stage for decades of debate about this robust cousin of ours. But for all the thick jaws and molars that turned up in the sites across eastern Africa, there was a striking silence when it came to the rest of the body. For more than half a century, almost nothing of Paranthropus from the neck down was known with confidence. Then, in 2013, a team led by Manuel Dominguez Rodrigo described a partial skeleton from Olduvai, designated 𝐓/𝐻 that suddenly cracked open a window. Scattered and fragmentary, yes, but still enough to remind us that these beings were not just skulls in textbooks, but walking, breathing primates who carried their bodies across the Rift Valley plains. The skeleton was discovered in Bed 2 of Olduvai Gorge, in deposits dating to roughly 1.34 million years ago. The site had already yielded the familiar robust jaws and teeth of Paranthropus 𝐓𝐾𝐌𝐏𝐒, and now postcranial fragments lay beside them. What was uncovered included parts of arms, hands and legs, alongside dental remains that carried the unmistakable stamp of robust morphology. The association was key. Without teeth, the attribution might have been impossible, because limb bones often overlap in form between species. But here, the powerful molars and cranial fragments gave context, anchoring the postcranial pieces to a specific lineage. The reveal here lies in what these bones tell us about the locomotion and life of Paranthropus. For decades, reconstructions of Paranthropus bodies had relied on inference, sometimes even on Australopithecus skeletons such as the famous Lucy, sometimes on Homo erectus, depending on which trait seemed more plausible. Some thought the robust skulls sat atop relatively primitive bodies, climbing trees often. Others imagined more modern proportions. 𝐓/𝐻𝐒 suggests that Paranthropus was fully terrestrial, walking upright with long legs suited for covering ground. The limb proportions, although fragmentary, indicate that they were not awkward bipeds, but efficient walkers. This matches the ecological picture we have from isotopes, creatures who foraged widely across open grasslands and wetlands, not tree dwellers hiding in the canopy. But the story is not that simple. The humeral fragments from 𝐓/𝐻𝐻 show robusticity, meaning strong bone thickness and muscle attachment sites. This suggests heavy use of the arms, perhaps for digging or manipulating plant matter. The hand bones, though incomplete, hint at strong grips, not the delicate precision of later Homo, but forceful and functional. The femur and tibia, where preserved, suggest weight-bearing consistent with bipedal locomotion. Taken together, this paints a picture of a body built for endurance on the ground, but also for laborious tasks requiring strength. Why does this matter? Because without postcranial remains, it is easy to reduce Paranthropus to caricatures of chewing machines, defined only by their jaws. The skeleton reminds us that they were whole beings, adapted across their anatomy to a way of life. They walked upright like us. They carried weight on their hips and knees like us. Their arms and hands were powerful, engaged in activities that archaeology can only guess at. They were not partial creatures. They were complete. The rarity of such a find cannot be overstated. Teeth preserve well because they are hard and resistant. Skull fragments can survive burial and erosion, but limb bones are more fragile, often scattered or destroyed by carnivores, water, or time. To have postcranial remains securely linked to Paranthropus 𝐓𝐾𝐌𝐏𝐒 is extraordinary. Before 𝐓/𝐻𝐻𝐒, debates about their body shape relied on indirect arguments. Some pointed to the thick enamel and cranial crests, and suggested they must have had equally stocky builds. Others suspected gracility. The truth, as the bones suggest, is somewhere in between, robust in strength but not clumsy, upright in gait but not quite human in finesse. Even with this discovery, humility is required. 𝐓/𝐻𝐻𝐒 is partial and incomplete. We cannot reconstruct height with precision. Estimates suggest an individual of medium stature, but the variation in Paranthropus populations could have been wider. Sexual dimorphism, differences between males and females, likely played a role. Males may have been larger and more robust, females smaller. Without a larger sample, we cannot generalize. The skeleton provides a glimpse, not a complete photograph. Another striking detail is the depositional context. The remains were found in sediments that also contain stone tools of Acheulean type and animal bones with cut marks. This raises the question of association. Were Paranthropus present at the site during tool use? Or are their bones mixed into a palimpsest created by multiple hominin groups? The conservative answer is that Paranthropus lived in these landscapes and died in these same sediments, but whether they wielded the tools themselves is unresolved. What matters here is not tool culture, but the affirmation that Paranthropus lived side by side with other hominins in a landscape of overlapping activities. For paleoanthropology, 𝐓/�80 is a milestone because it grounds reconstructions in evidence rather than speculation. It allows biomechanical analysis, however limited. The cross-sections of long bones show cortical thickness, patterns of stress and strain that speak to habitual activities. Robusticity suggests strenuous lives, bones remodelled by daily force. These were not sedentary creatures but active foragers, constantly moving and working to extract energy from a challenging environment. The haunting question remains, why do we have so little of them? For a lineage that lasted nearly 1 million years, Paranthropus left an abundance of jaws and teeth, but almost no bodies. This bias may reflect taphonomy, the processes of decay and burial. It may reflect where paleoanthropologists have focused their excavations. Or it may be sheer chance, the cruel lottery of fossilization. Whatever the cause, the scarcity of skeletons has kept Paranthropus somewhat ghostly in our imagination. 𝐓/80 is a rare anchor, a reminder that they were not abstractions but flesh and bone creatures. The implications ripple beyond anatomy. Knowing that Paranthropus was upright, mobile and robust reshapes how we think about their ecological role. They were not trapped in small habitats, but likely ranged widely. They were not weaklings confined to fallback foods, but strong-bodied beings who endured through tough seasons. Their extinction, when it came, cannot be attributed to anatomical inadequacy. Instead, it must be sought in environmental and ecological shifts, as we have already begun to explore. And yet, in the end, we must accept the limits of knowledge. One skeleton, however precious, cannot tell the full story of a lineage spread across thousands of kilometres and hundreds of thousands of years. It tells us that Paranthropus walked like us, that their arms bore strength, that their bones were shaped by work. It does not tell us the details of their daily lives, their social structures or their thoughts. It leaves us with a mixture of revelation and yearning. So we return to the haunting question with which we began. What does one shattered skeleton tell us about a whole vanished lineage? It tells us that they were not simply skulls in museums, but beings who bore their weight on sturdy legs, who used their arms to labour, who walked the same Rift Valley ground that we now study. It tells us that even the most specialised of creatures were whole, complex and resilient, and it tells us that sometimes one fragile set of bones can make a lineage come alive again, if only for a moment, before the silence of the fossil record closes around it once more. Did Homo erectus actually get first access to the buffet? That is the central question raised by a remarkable site in 𝐓𝐈𝐌𝐄𝐒𝐒 Gorge known as Juma's Korongo II, or JK2. Between 1.3 and 1.0 million years ago, this ravine held not only stone tools and bones, but also the taphonomic signatures that allow us to ask who reached a carcass first, how they processed it, and what that meant for survival. For decades, the hunter versus scavenger debate has swirled around early Homo. Were they opportunists who waited for lions to finish and then snapped up leftovers? Or were they capable of coordinated hunts, bringing down animals far larger than themselves? JK2 provides one of the clearest pieces of evidence that, at least some of the time, Homo erectus had primary access to big game meat, including hippos, giraffes, and large bovids. And if they did, that changes how we understand both their diets and their social worlds. The site itself lies on the northern side of 𝐓𝐈𝐌𝐄𝐒𝐒 Gorge, about 2.5 kilometres from the confluence of the main gorge and side gorge. First noticed during Louis Leakey's early expeditions in the 1930s, the sediments belong to Bed 3, which spans the late Lower Pleistocene. Archaeologists have recovered thousands of bones and lithics from this context, but it is the detailed taphonomic analysis that matters most. In 2020, José Ravedra and colleagues revisited the assemblage, examining over 1,500 postcranial bones to tease apart the sequence of marks left by stone, tooth, and time. Their conclusion was clear. The accumulation of bones was not natural, nor primarily the work of carnivores. Instead, cut marks and percussion scars show that hominins were the main agents of deposition, accessing carcasses early, breaking bones for marrow and leaving behind a record of deliberate butchery. The reveal lies in the distribution of marks. When carnivores feed first, they typically target the ends of long bones, leaving punctures, scores, and gnaw marks where muscle attachments are thickest. Humans arriving later leave cut marks mostly on scraps, or none at all because little meat remains. At JK2, the pattern is reversed. Cut marks cluster on the shafts of long bones, the richest areas for meat, while tooth marks are concentrated at the ends. This indicates that hominins processed the carcasses before carnivores had their chance, removing substantial flesh and marrow. Percussion marks from hammerstones show that bones were deliberately cracked open, not simply trampled or broken by chance. It was a buffet, and Homo erectus was seated first at the table. What makes this significant is the size of the animals involved. The faunal assemblage includes hippos, giraffes, and large bovids, all animals that require strategy to exploit. Hippos in particular are dangerous prey, territorial and aggressive, weighing over a ton. To secure hippo meat suggests cooperation and planning. Whether through active hunting or opportunistic exploitation of vulnerable individuals, early Homo was clearly capable of mobilizing groups, wielding Acheulean tools, and sustaining the risks of big game acquisition. This marks a step beyond the sporadic scavenging scenarios once favoured. It also fits with a broader pattern emerging from sites across Africa. By this period, Acheulean hominins were increasingly confident large-game consumers. The information encoded at JK2 also underscores the importance of meat in the Homo erectus diet. Meat provides dense calories, fats, and micronutrients essential for growing brains. Cooking is not yet securely evidenced at this time, so raw or lightly processed meat was likely consumed. The cut marks tell us that muscle was stripped systematically, marrow extracted, and possibly grease rendered from bones. These behaviours reflect a deepening commitment to animal resources, complementing plant foods, but shifting the nutritional balance toward higher quality diets. The evolutionary consequences were profound. More energy available for brains, less need for massive guts, and a trajectory toward the human form. The context of Acheulean handaxes at JK2 reinforces this interpretation. Symmetrical bifaces and cleavers were recovered alongside the bones, tools shaped with dozens of controlled flakes. Their edges were ideal for butchering large animals, slicing through hide and muscle. The sheer number of flakes removed to create each tool shows forethought and skill. These were not casual expedients, but carefully shaped implements, designed to be effective at jobs like dismembering hippos. It is difficult to imagine a clearer link between technology and subsistence. Acheulean tools were the knives and cleavers of their day, and JK2 demonstrates that they were used on big game carcasses. Yet we must be cautious. Taphonomy is interpretive, not photographic. While the evidence strongly suggests primary access, it cannot always distinguish between active hunting and very early scavenging. Perhaps Homo erectus did not bring down a hippo directly, but seized it quickly after a natural death or a predator's initial strike. The line between hunting and aggressive scavenging may blur in these contexts. What matters, though, is timing. Hominins were not consistently relegated to scraps. They were players at the top of the food chain, not merely followers. Even if they sometimes capitalized on opportunities, they did so in ways that left them with the best portions. What does this tell us about their social world? Hunting large animals requires coordination, communication, and risk-sharing. While language as we know it likely did not exist, gestures, vocalizations, and shared traditions could have supported cooperation. The very presence of cut-marked hippo bones implies not just skill, but bravery. To engage with such prey means trusting your group, dividing labour, and perhaps sharing meat afterward. JK2 is therefore not only a record of diet, but of society. It hints at bonds forged in action, meals divided at campsites, knowledge transmitted across generations about where to find, how to approach, and how to process dangerous animals. As with all science, humility is essential. JK2 is one site, one glimpse into a long span of time. Other assemblages suggest variability. Sometimes Homo erectus may have scavenged more, sometimes less. Local conditions, group size, and prey availability all shaped outcomes. But the balance of evidence from JK2 tilts strongly toward active engagement with large animals. It reinforces a picture of Homo erectus as adaptable, capable, and bold, a lineage that did not just survive but reshaped its ecological niche through ingenuity and cooperation. The haunting question is this: how much of our own humanity was born around carcasses like these? When early humans cracked bones with hammerstones and shared marrow, were they also cracking open new ways of living together? Was the hippo at JK2 not just food, but a catalyst for bonds, roles, and traditions that echo faintly even now when we gather around meals? We cannot know for certain. All we can say is that 1 million years ago, in a gorge carved by time and water, our ancestors stood at the buffet of life, not timid scavengers but confident participants, and left behind bones that still tell their story. What do crude, heavy hand axes say about early cognition? To stand in front of the artifacts from Khonso in southern Ethiopia is to face this question directly. Around 1.75 to 1.6 million years ago, the first recognisably Acheulean tools appear here, and they are not the neat symmetrical showpieces we see in later collections. Instead, they are thick, heavy, sometimes little more than a flake removed from a boulder and given a few extra strikes. Yet even in this crudeness lies a revelation. For the first time, hominins were shaping stone with an image in mind, imposing form rather than simply reacting to the rock's edges. At Khonso, we witness a moment when cognition shifted from expediency toward planning, when Homo erectus began to think not just about what a stone was, but what it could become. The Khonso Formation, stretching across the southwestern end of the main Ethiopian rift, preserves a geological record from nearly 1.9 to just under 1 million years ago. Within these deposits, archaeologists have uncovered an extraordinary sequence of stone tools, each horizon anchored by volcanic tuffs dated with precision. The earliest Acheulean assemblage appears at KGA6, just above the KYT2 tuff, which itself has been radiometrically dated to about 1.74 million years ago. This makes Khonso's tools among the very oldest handaxes on Earth, contemporary with the 𝐓𝐈𝐌𝐄𝐒𝐒 assemblage in Kenya. What makes Khonso unique is not just the age but the continuity. From its earliest heavy picks to later, more refined handaxes, the sequence tracks the gradual unfolding of Acheulean technology over hundreds of thousands of years. At the dawn of this tradition, however, refinement was not the point. The earliest Khonso tools are dominated by large picks made on thick flake blanks, some exceeding 20 centimetres in length. These picks are angular, trihedral in cross-section, sometimes with a pointed tip created by abrupt flaking. Alongside them lie handaxes, but these are crude, with low flake scar counts, minimal symmetry and thick edges. They are not yet the iconic teardrop forms we associate with later Acheulean. Instead, they are attempts, serious, intentional, but still hesitant. And yet, the intention is undeniable. These are not simple cores knocked opportunistically for flakes, as in older one technology. They are large cutting tools, shaped with an aim in mind, however roughly achieved. The reveal here lies in what this shift implies about cognition. To create a hand axe, even a crude one, requires visualizing a future shape and striking flakes in a sequence that guides the rock toward that form. It is not random battering, but ordered action. At Khonso, the artisans may not have achieved elegance, but they demonstrated something more profound: the capacity for predetermination. This is the difference between reacting to a problem and imagining a solution. It marks a turning point in how hominins interacted with their material world. The information gleaned from Khonso's sequence also shows the diversity of early Acheulean forms. Picks and handaxes coexisted from the start. Picks, with their heavy points, were likely used for digging or heavy-duty work, perhaps prying roots or breaking into marrow-rich bones. Handaxes, with their broader cutting edges, suited slicing tasks like butchering carcasses. The coexistence of both types suggests functional differentiation, not a single type of tool, but a toolkit. Even at this early stage, Homo erectus was building an adaptive repertoire, experimenting with forms to solve different problems. The imposition of form was not uniform but varied, reflecting both function and the limits of knapping skill. What is striking is the gradual increase in workmanship through time. By 1.6 million years ago, the Khonso handaxes show greater thinning and improved symmetry. Flake scar counts rise, edges become straighter, and tips more pointed. But even then, they remain thick by later standards, with sinusoidal cutting edges that speak to limited control. This gradual refinement tells us that the Acheulean was not an invention fully formed, but an unfolding experiment, stretched across hundreds of millennia. Each generation of nappers inherited techniques from the last, slowly ratcheting up skill and precision. For scientists, 𝐶𝐿 importance lies in its stratigraphic clarity. The volcanic tuffs bracketing the tool layers allow us to place each assemblage in time with unusual accuracy. This makes it possible to chart not just what tools looked like, but when specific changes appeared. The earliest crude bifaces date to about 1.75 million years ago. By 1.6 million years ago, refinement is evident. By 1.4 million years ago, handaxes become thinner and more symmetrical. This temporal sequence provides a rare chance to watch cognition evolve, not in leaps, but in increments, visible in the scars of stone. Still, humility is necessary. We cannot look into the minds of the 𝐶𝐿 nappers. Did they see their crude handaxes as flawed attempts or as perfectly functional tools? The modern eye may judge them crude, but to those who made and used them, they were effective. The imposition of form was not about beauty, but utility. Function came first, and function was achieved. The question of cognition arises not from our aesthetic standards, but from the repeated intentional shaping across sites and generations. That persistence shows that hominins recognize the value of shaping large flakes into standardized forms. There is also the question of social learning. Handaxe making is not intuitive. Experimental nappers today struggle to achieve symmetry without guidance, often requiring years of practice. For early Homo to sustain the Acheulean tradition, knowledge must have been transmitted. Whether through demonstrations, imitation, or some form of teaching, skills passed from one set of hands to another. At 𝐶𝐿 we glimpse not just individual cognition but shared culture, however rudimentary. These heavy handaxes and picks are therefore fossils of social as well as technical behaviour. What did it feel like to wield one of these first big blades? Imagine gripping a basalt handaxe, rough-edged but weighty, in the Rift Valley 1.7 million years ago. The stone fits awkwardly but functionally into the palm. It is heavy enough to split a joint, sharp enough to cut through tendon, blunt enough to crush. To strike with it is to amplify muscle with stone, to extend the body into a tool. The first handaxe was not elegant, but it was revolutionary. It allowed Homo erectus to act on the world with force and precision beyond bare hands. It was both weapon and utensil, both hammer and knife. The haunting question is this: what changed in the minds of our ancestors to make them imagine a shape within stone? Was it necessity, a response to new prey and landscapes? Was it chance, a discovery repeated until tradition formed? Or was it the gradual accumulation of small cognitive shifts, each napper adding a new layer of control? We cannot answer with certainty. All we can say is that by 1.75 million years ago, in the dusty beds of 𝐶𝐿, humans began to leave behind tools that spoke not only of need, but of thought. Crude though they were, they mark the dawn of a tradition that would last for more than 1 million years, carried from Africa to Asia and Europe, shaping both landscapes and minds along the way. Why didn't the picks change much while the handaxes did? That is the quiet puzzle that emerges when we look at the Acheulean record from 𝐶𝐿 between 1.6 and 1.2 million years ago. In these horizons, archaeologists found hundreds of stone implements, all carefully dated by volcanic tuffs and magnetostratigraphy, allowing us to watch technological change over time. The handaxes in this period became thinner, more symmetrical and more refined, while the picks remained stubbornly similar to their earliest forms. It seems that in one tradition, refinement was prized, while in the other, continuity carried the day. Understanding this divergence is not just about rocks, it is about cognition, function, and even the first stirrings of style. The reveal lies in the details of the 𝐶𝐿 assemblages, at sites such as 𝐓𝐈𝐌𝐿𝐿4, 𝐓𝐓𝐿7, and 𝐓𝐓𝐿10, dating from roughly 1.6 to 1.4 million years ago. The handaxes show a clear trend toward increased flake scar counts, straighter edges, and more carefully thinned tips. They still lack the elegance of later Acheulean pieces, but compared to the heavy, crude tools of 1.75 million years ago, they are markedly more sophisticated. The artisans struck more flakes, sometimes 20 or more, to shape edges, reduce thickness, and impose bilateral symmetry. By 1.25 million years ago at 𝐏𝐒/12, handaxes approach recognizable teardrop forms. This trajectory suggests an ongoing experiment in refinement, each generation learning from the last, striving to produce more effective cutting tools. By contrast, the picks tell a different story. From the earliest crude forms at 1.75 million years ago to those of 1.4 and 1.25 million years ago, the shape remains consistent. They are large, thick trihedral tools with pointed ends. Flake scar counts remain low, modification minimal, symmetry absent. Their tips are sometimes notched, producing a distinctive bent profile that recurs across layers. This continuity suggests that function, not aesthetics, determine their form. A pick is heavy by design. Its job is to dig, to pry, to smash. It does not need symmetry to be effective. To thin it would weaken it. In this way, the picks embody a technological conservatism. They changed little because they were already fit for purpose. This contrast tells us something about cognition. Where refinement improved function, as in cutting tools, hominins pursued it. Where refinement offered no advantage, as in digging tools, they did not. This shows flexibility of thought, a willingness to invest energy where it mattered, and to preserve tradition where it did not. It also hints at an early sense of style. The notched tips of picks repeated across time may have carried symbolic or habitual value. Archaeologists debate whether this is evidence of cultural tradition, but at the very least it reflects consistency beyond raw necessity. When a shape recurs across hundreds of thousands of years, we must at least wonder if some aspect of identity or habit was encoded in the stone. The broader context reinforces this. Across Eastern Africa, Acheulean sites of this age show similar patterns: refinement in handaxes, stability in picks. This is not unique to Conso, but part of a continental trend. It suggests that Homo erectus groups spread across vast distances maintained both flexibility and conservatism in their toolkits. They shared a mental template for what a handaxe should become and for what a pick should remain. Such templates imply teaching, imitation, and a social transmission of knowledge. Tools were not just objects, but carriers of memory, linking generations through shared practice. The information embedded in these stones also tells us about daily life. Handaxes were likely used for butchering large animals, slicing meat, and processing hides. Their refinement would have made them sharper, easier to handle, more efficient in reducing carcasses. Picks, by contrast, were used for heavy-duty tasks such as digging tubers, breaking wood, or smashing bones. Their unchanged form suggests that these tasks did not demand refinement, only strength. Together, the two tool types show a division of labour in technology: light cutting versus heavy breaking, refinement versus resilience. It is tempting to see in this the earliest stirrings of specialisation, not in individuals but in objects. And yet we must remain humble. The stones do not tell us everything. They cannot reveal the hands that made them, the teaching moments, the failures, the discarded cores. They do not show us how tools were hafted or carried, how often they were resharpened, how they fit into the rhythm of life. What they do show, however, is a pattern of thought across time, a balance between innovation and tradition. This balance is perhaps one of the deepest traits of humanity, the urge to improve tempered by the comfort of continuity. The haunting question is this: were the hominins of Conso aware of the difference between change and continuity in their tools? Did they notice that their handaxes were becoming thinner, more symmetrical, while their picks remained constant? Or was this process invisible to them, unfolding slowly across generations without conscious recognition? We cannot know, but in either case, the stones preserve the duality of human invention, the drive to refine and the willingness to repeat. In that duality, we glimpse a mind both restless and rooted, a mind that would one day shape not only stones but stories. Was fire discovered, borrowed, or just hidden in a cave? This question takes us to Wonderwerk Cave in South Africa, where a layer of soil buried some 30 metres inside the entrance has become one of the most debated pieces of evidence in the history of humanity. Around 1 million years ago, hominins were living in this cave, leaving behind Acheulean handaxes, flakes, and the bones of animals they processed. Within this archaeological horizon, excavators also found tiny flecks of ash, burned bone fragments, and mineral signatures that only occur when plant matter has been heated to high temperatures. To see such traces so far inside a cave is to confront the possibility that fire was not just stumbled upon outdoors but carried, tended and sustained in the dark. The reveal lies in the microscopic evidence. Ash is fragile, easily blown away or washed out. At Wonderwerk, however, thin layers of silty soil preserved delicate plant ash that could not have drifted in from outside. Spectroscopic analyses show that these particles have been heated to several hundred degrees Celsius, consistent with burning inside the cave. Alongside them lie bone fragments with colour changes diagnostic of exposure to fire, some blackened, some calcined into a chalky white. These bones were not randomly scattered but associated with stone tools, suggesting they formed part of a living floor where hominins were working, eating, and perhaps experimenting with flame. For archaeologists, such evidence offers one of the earliest credible claims for controlled fire use by humans. The information becomes more compelling when we consider the cave's depth. 30 metres from the entrance is too far for sunlight to reach, too sheltered for natural grass fires to blow sparks inside. If burning took place here, it was because hominins brought combustible material in and maintained it. That does not necessarily mean they could create fire from scratch. The most cautious interpretation suggests they borrowed fire from wild sources, carrying smouldering branches or embers, and keeping them alive for hours or days. Even this, though, would be a milestone. To maintain fire indoors is to transform a cave from a shelter into a hearth, to change darkness into light, and to alter the relationship between humans and their environment. We must also face the debates. Fire leaves ambiguous traces, and the earliest evidence is often contested. Could the burned material at Wonderwerk have been produced by natural processes, such as lightning strikes igniting vegetation near the entrance and smoke drifting inward? Some researchers have suggested this possibility, yet the spatial pattern of the ashen bones, the repeated association with tools, and the absence of other signs of flooding or disturbance argue against it. The most parsimonious explanation remains that hominins were managing fire inside the cave. Even so, scientists acknowledge the uncertainty. Controlled fire use is a continuum, not an on-off switch. Were these flames deliberate hearths, or opportunistic blazes tended briefly before dying out? Did hominins know how to reignite fire if it went out, or were they dependent on waiting for the next lightning strike? These questions remain unanswered. What matters is that Wonderwerk provides a rare glimpse into the experimental phase of humanity's relationship with fire. By 1 million years ago, Homo erectus and its relatives were already expert toolmakers and hunters. Fire, however, was a new element, unpredictable and dangerous. To bring it inside a cave was an act of both practicality and courage. The warmth would have been welcome in cooler nights. The light would have extended activity into darkness. The flames may even have helped ward off predators at the cave mouth. Whether by design or by accident, the cave became a container not just of people, but of the first domestic flame. The implications are profound. Ashes and bones at Wonderwerk suggest that fire was not just encountered, but integrated into daily life. This sets a precedent for later, more widespread fire use seen by 400,000 years ago in Europe, Israel and China. At those later sites, hearths, charcoal, and burned sediments leave no doubt that fire had become a habitual technology. At Wonderwerk, we stand at the threshold, where fire is still fragile, still contested, but already transformative. As humble scientists, we must admit what we cannot know. We do not see hearth rings, structured fireplaces, or clear evidence of repeated burning events at Wonderwerk from 1 million years ago. Those appear later. We cannot reconstruct the gestures of the hands that fed twigs to embers or shielded flames from wind. All we have are mineral traces, ash particles, and bones. But those are enough to say, with some confidence, that hominins were beginning to experiment with flame, to bend its wild energy into something they could keep. The haunting question is this: did they know what they had started? To sit in darkness while fire flickers on the walls is to see shadows dance, to hear the crackle of fuel, to feel heat on the skin. Did those first humans sense that this was more than warmth, more than light, that it was a doorway to an entirely new way of life? We cannot enter their minds, but we can recognize the threshold they crossed. Fire indoors was not inevitable, It was a choice, a risk, an experiment. And in the soil of Wonderwerk Cave 1 million years ago, the embers of that choice still glow faintly today. What did it mean when a stone edge touched flesh? To place yourself in East Africa between 1.7 and 1 million years ago is to see a landscape where bones and stones record the intimate story of survival. The first evidence of deliberate butchery, recognisable in cut marks etched into animal bones, tells us that Homo had entered a new ecological niche. These marks are not vague scratches left by chance. They are systematic incisions, oriented in ways that correspond to the removal of flesh, the disarticulation of joints, and the breaking open of long bones for marrow. In those gestures lies a transformation of diet and behaviour that altered both bodies and minds. The reveal is not just that meat was eaten, but that it was obtained and processed in deliberate, organised ways. At sites across Kenya, Tanzania and Ethiopia, spanning from the late Oldowan into the Acheulean, archaeologists have recovered thousands of bones carrying human signatures. The hum of deep time comes alive in these traces, a groove along a bovid rib where a flake sliced through muscle, percussion scars on femurs where hammerstones fractured shafts to reach the fat-rich marrow. These are not random acts. They form recurring patterns across sites and time, suggesting that early humans had developed a cultural repertoire for turning carcasses into meals. The information from taphonomic studies is striking. Bones gnawed by carnivores have different signatures: punctures, furrows, and spiral fractures caused by teeth. In contrast, cut marks from stone tools are V-shaped in cross-section and oriented along muscle attachments. Experimental butchery with replica tools confirms the patterns. When a sharp flake is drawn down a bone to remove flesh, the resulting incision matches those seen in fossils at 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 or 𝐓𝐈𝐌𝐿𝐿𝐄𝐒𝐒. When a hammerstone strikes a long bone to crack it open, percussion notches and flakes mirror those found on ancient assemblages. Through these comparisons, archaeologists can reconstruct not just that meat was eaten, but how it was acquired and processed. This shift to regular meat consumption had profound consequences. Animal tissue is dense in calories and nutrients, particularly fats and proteins critical for brain development. Marrow, in particular, is rich in lipids that provide long-lasting energy. To break open bones is to access a resource that carnivores themselves prized, one that would have sustained hominin groups through lean seasons. The repeated evidence of marrow extraction suggests that Homo was not passively scavenging leftovers, but actively seeking high-value resources, even from partially defleshed carcasses. Some sites indicate early access, where cut marks overlay tooth marks in ways that show humans got to nutritious parts before hyenas or lions. Others show later access, where marrow was extracted after predators had taken the flesh. Both strategies reveal adaptability and persistence. One of the most instructive regions is Olduvai Gorge. Across beds the Fall 2 and 3, thousands of bones have been excavated with cut marks and percussion scars. In earlier Oldowan contexts, hominins seem to have focused on small and medium-sized ungulates, perhaps scavenging as often as hunting. By the Acheulean horizons, however, evidence suggests more frequent access to larger carcasses, including hippos and giraffes. At sites like 𝐓𝐿𝐾𝐌𝐏𝐒, and others, the density of butchered remains indicates repeated use of locales for processing kills. These places became landscapes of memory, where generations returned to harvest meat and marrow, leaving behind the archaeological palimpsest we study today. 𝐓𝐈𝐌𝐿𝐄𝐒𝐒 in northern Kenya tells a similar story. Here, cut marks appear on diverse taxa, from antelopes to elephants. Experimental studies show that many of the marks correspond to dismembering limbs, skinning, and defleshing large portions of meat. Percussion marks on elephant bones suggest that even massive carcasses were exploited, though whether humans brought them down or scavenged them remains debated. Either way, Homo groups learned to capitalize on opportunities, whether through cooperation in hunting or tenacity in scavenging. Butchery marks also tell us something about skill. To disarticulate a joint with a sharp flake requires knowledge of anatomy, awareness of where ligaments hold bones together. To maximize marrow extraction without shattering the nutrient-rich interior takes precision. Over time, cut mark patterns suggest increasing efficiency. Later Acheulean sites show fewer but more effective incisions, as if butchers had refined their techniques. This progression hints at learning across generations, at knowledge transmitted within groups. It is not just the stones that were shaped, but the hands and minds that wielded them. The marrow question has been particularly revealing. Percussion marks on long bones are ubiquitous at Acheulean sites. Experimental archaeology has shown that to extract marrow, bones must be struck in particular ways that maximize access without shattering fragments into useless splinters. At sites dated between 1.5 and 1 million years ago, the frequency and placement of percussion marks indicate systematic marrow processing. This is not opportunism, but routine behaviour, suggesting that marrow was an established part of the diet. It also implies planning. Bones may have been transported to central places where groups shared and consumed resources. The social implications are profound. Meat and marrow are divisible resources, easily shared among individuals. Unlike tubers or small prey consumed immediately, a large carcass requires distribution. Sharing meat may have fostered cooperation, strengthened social bonds, and created expectations of reciprocity. The archaeology does not show us conversations or rituals, but it does show us piles of bones accumulated in central places. Those piles suggest gatherings, cooperation in carrying, and communal consumption. To eat meat was to become entangled in new social dynamics, ones that shaped human evolution as much as biology. The haunting question is what this meant for identity. When a stone edge touched flesh, it marked more than calories gained. It marked the crossing of a threshold in how humans interacted with their environment. Meat was no longer just scavenged scraps, but an anticipated, sought-after part of the diet. The marks etched on bone record not only survival, but intention. They show minds that saw an animal not just as a moving body, but as a store of resources waiting to be unlocked. Did those early humans feel pride in a successful butchery, relief in cracking marrow from a femur, or obligation in sharing food with their companions? We cannot know, but the bones whisper of those possibilities. As humble scientists, we must admit the limits. Cut marks alone cannot tell us whether hominins hunted or scavenged in every case. They cannot reveal the sounds, the smells, the taste of roasted or raw meat. They do not preserve the laughter, the arguments, or the hunger of those who gathered around carcasses. But they do preserve a record of contact, stone against flesh, flake against bone, that was repeated across landscapes and centuries, and in that repetition we see a pattern that transformed our lineage. How do ice sheets in the north end up deciding who survives in Africa? That is the strange reality of the mid-Pleistocene transition, the shift that began around 1.3 million years ago and unfolded until roughly 900,000 years ago. It is a story that links the slow beat of orbital cycles to the precarious fate of grasses and rivers, woodlands and lakes, and ultimately to the survival strategies of early humans and the animals that shared their landscapes. The paradox is that glaciers thousands of kilometres away in the northern hemisphere controlled rainfall on the African savannas, where Homo erectus searched for food. Climate roulette had begun, and its wheels spun on timescales far larger than any human lifetime. The reveal begins with the mechanics of Earth's orbit. For most of the earlier Pleistocene, the dominant rhythm of global climate followed 41,000-year cycles tied to the tilt of the Earth's axis. These were regular, predictable shifts, oscillations between warmer interglacials and cooler glacials, but of a scale that ecosystems could usually adapt to. Around 1.2 million years ago, however, a profound reorganization began. The glacial cycles lengthened, shifting toward 100,000-year intervals. Ice sheets in the northern hemisphere grew larger, lasting longer before collapsing into interglacial warmth. The reasons for this transition remain debated. Changes in greenhouse gases, feedbacks from ice sheet dynamics, and shifts in deep ocean circulation all played roles. What matters for our story is that the climate became less predictable, with longer periods of aridity punctuated by abrupt returns of wetter conditions. The information from African lake cores and marine sediments captures the impact. In the East African Rift, sediments preserve alternating bands of pollen, diatoms, and dust that reveal vegetation turnover at unprecedented rates. One moment, the Rift Valley might host expansive grasslands rich in grazing animals. The next, woodlands surged as rainfall patterns shifted. In some intervals, lakes expanded dramatically, flooding rift basins and supporting lush aquatic ecosystems. Then, just as suddenly, they contracted or dried, leaving behind saline flats and dust storms. This instability is the hallmark of the mid-Pleistocene transition in tropical regions. It was not simply drier or wetter on average, but more variable, a roulette of habitats spinning with each orbital beat. For herbivores, this meant an uncertain menu. Specialists dependent on consistent grass cover, such as some grazing bovids, and indeed Paranthropus with its heavy jaws tuned to C4 plants, found themselves squeezed by shrinking grasslands and expanding woodlands. Generalists that could browse as well as graze fared better. The faunal record shows turnovers in East Africa during this period, with new species appearing and others vanishing. For humans, this meant constant adaptation. Homo erectus was a versatile forager, capable of consuming both plant and animal resources, and that flexibility was tested as climates swung. One striking piece of evidence comes from the Olorgesailie Basin in Kenya. Layers of sediments deposited during this period record alternating wet and dry phases, sometimes on scales of a few thousand years. Within these layers, Acheulean tools and butchered bones appear and disappear, showing that human occupation was tied to water availability and vegetation. When lakes were present, animals gathered and humans followed, leaving behind dense scatters of artifacts. When lakes dried, the basin was abandoned and windblown sediments accumulated. This on-off pattern reflects the boom and bust ecology imposed by orbital cycles, making survival a matter of tracking shifting habitats rather than staying in one place. Ocean cores reinforce the picture. Dust blown from Africa into the Atlantic waxed and waned with climate cycles, peaking during arid phases when vegetation contracted. These dust signals align with Northern Hemisphere ice sheet growth, showing the teleconnection between distant glaciers and African rainfall. In other words, when ice expanded in Europe, monsoons weakened over Africa, drying the rift. When ice retreated, rains returned. The roulette wheel spun not in Nairobi or Olduvai, but in the frozen north, yet its consequences were felt on every hillside where early humans gathered tubers or butchered carcasses. The implications for human evolution are profound. Variability demands flexibility. A lineage that could only survive in one environment was doomed to vanish when that environment disappeared. A lineage capable of exploiting shifting resources had a chance to endure. The mid-Pleistocene transition was thus not just a background event, but a forcing mechanism that shaped cognitive and behavioral traits. Planning for uncertainty, maintaining mobility, developing broad diets, these were not luxuries but necessities in a world where habitats transformed within a few generations. Yet as humble scientists, we must admit that the evidence remains incomplete. Sediment cores, pollen diagrams, and isotope records give us broad strokes, but the details of how individual groups of humans experienced these changes remain elusive. Did they migrate seasonally, following rivers and herds? Did they maintain knowledge of refuges that held water in dry years? Did they experience population crashes during prolonged droughts, only to rebound when conditions improved? We can model scenarios, but we cannot hear their voices. The haunting question remains whether climate roulette acted more as a filter or as a teacher. Did the volatility simply wipe out those who could not adapt, leaving the survivors by chance? Or did it actively push Homo populations to innovate, to refine tools, to expand social networks, to think ahead in new ways? The answer is likely both. What we can say is that from 1.3 to 900,000 years ago, the rules of the game changed. Glacial cycles lengthened, climates swung more violently, and the landscapes of Africa became unstable theatres where humans had to improvise. Out of that improvisation would come resilience, and perhaps the seeds of the creativity that later defined us. Why did a giant grass-eating baboon almost beat us at our own game? That is the strange story of Therapithecus, a primate that roamed Africa from about 2 million to 1 million years ago and lived alongside the earliest members of our genus. If you were walking through the Rift Valley in those times, you would not have seen only hominins cutting meat from bones or Paranthropus gnawing on tubers. You would also have seen enormous baboons with long snouts, tall limbs, and a lifestyle surprisingly similar to some of our own ancestors. 𝐓𝐈𝐿𝐼𝐼 was not a small forest dweller. It was a plains primate, grazing in large troops across the savannas, consuming the same C4 grasses and sedges that sustained antelope, zebras, and, most intriguingly, Paranthropus boisei. The reveal begins with teeth. Fossil jaws of 𝐓𝐈𝐿𝐼𝐼 show high-crowned molars covered in thick enamel, perfectly adapted for grinding tough grasses. Stable isotope analyses confirm that their diet was dominated by C4 plants, the same chemical signature that defines grass-based foods. This makes them one of the few primates to specialize so heavily on grasses, a strategy very unusual for monkeys and apes. In modern ecosystems, primates are typically omnivores, browsing on fruits, leaves, insects, and occasional small prey. To build a lineage around grasses is unusual and risky. Yet 𝐓𝐈𝐿𝐼𝐼 succeeded for a long stretch of the Pleistocene, evolving into a grazing specialist that may have lived in enormous herds on the open plains. The information becomes even more intriguing when we compare 𝐓𝐈𝐿𝐼𝐼 to Paranthropus boisei. Both species carried the isotopic signatures of heavy grass reliance. Both had massive jaws and strong chewing muscles, reflected in the sagittal crests of Paranthropus skulls and the robust mandibles of 𝐓𝐈𝐿𝐼𝐼. Both were exploiting the same resource base: tough grasses, sedges, and underground storage organs in East African savannas. This overlap raises questions of competition. Was there room for two large-bodied primates with the same dietary strategy? Did the presence of 𝐓𝐈𝐿𝐼𝐼 intensify the pressures that eventually contributed to Paranthropus's decline? Paleo-ecological data suggests that 𝐓𝐈𝐿𝐼𝐼 was astonishingly successful for a long time. Fossil assemblages from sites such as Olduvai Gorge, Kubifora, and the Awash Valley frequently contain abundant 𝐓𝐈𝐼𝐼 remains, sometimes dominating primate faunas. Their presence indicates that they were not marginal players but central actors in Pleistocene ecosystems. Some reconstructions suggest they may have formed herds numbering in the hundreds, moving across open landscapes in ways more reminiscent of ungulates than primates. Such behaviour would have made them highly visible, powerful competitors for the grass resources that many other herbivores depended upon. The physiological adaptations of 𝐓𝐈𝐼𝐼 support this vision. Their large body size, approaching or exceeding modern geladas and baboons, would have given them digestive systems capable of processing vast amounts of fibrous plant matter. High-crowned teeth resist wear, allowing a lifetime of grinding grass. The fossils even show microwear patterns, consistent with repetitive abrasive chewing. They were, in essence, the primate equivalent of grazers like wildebeest. To see them on the landscape is to realize that hominins were not the only primates innovating with unusual diets. What makes the story more poignant is that 𝐓𝐈𝐼𝐼 is not entirely gone today. A single species survives, the gelada of the Ethiopian highlands, 𝐓𝐈𝐼𝐼 gelada. These modern primates live in large troops on grassy plateaus, feeding predominantly on blades of grass that they pluck with dexterous hands. Watching geladas graze today is like peering into a window of the past. They are the last representatives of a once diverse and widespread lineage. Their survival in the Ethiopian highlands reminds us that grazing primates were once far more common, and that for a time they nearly matched humans in ecological reach. The haunting question is why they did not last. From about 1 million years ago onward, 𝐓𝐈𝐼𝐼's diversity shrank, and their range contracted. Climate instability during the mid-Pleistocene transition likely played a role. As grasslands fluctuated, species specialized in grazing faced increasing risks. Flexible feeders such as Homo erectus could turn to meat, tubers, or fruits. Even generalist baboons could survive by shifting habitats. But 𝐓𝐈𝐼𝐼, committed to a grass diet, faced the narrowing of its ecological niche. In this sense, it shared the fate of Paranthropus boisei. Both were large primates tied to C4 resources, both flourished for over 1 million years, and both faded as climates shifted and competitors multiplied. What we see in 𝐓𝐈𝐼𝐼 is a reminder that the Pleistocene was not a stage built only for humans. It was an experimental arena where multiple primate lineages tested different strategies. Ours was not the only way to be a successful primate. One path led to the heavy-jawed Paranthropus. Another led to the grass-eating 𝐓𝐈𝐼𝐼. For long stretches they worked. Herds of grazing monkeys and groups of chewing hominins moved across the same savannas, perhaps eyeing each other warily at waterholes. But in the end, both strategies were vulnerable to the roulette of climate and the relentless competition of more flexible species. As humble researchers, we must recognise how little we know about their behaviour. Did Therapithecus show complex social systems like modern geladas, with hierarchies, alliances and grooming networks? Did they clash with the early humans over access to river valleys or patches of edible sedges? The bones do not tell us. We have only teeth, jaws and isotopes. Yet from these, we glimpse a primate that nearly wrote a very different chapter in primate evolution, one where grass-eating monkeys, not meat-eating humans, dominated the plains. What can footprints say that bones and tools never could? Fossils of teeth and skulls tell us about anatomy, and stone implements show us ingenuity, but only footprints offer a direct glimpse into movement, into the rhythm of bodies in motion on a particular day long ago. To step into a footprint preserved for over 1 million years is to see not only the shape of a foot, but also the pace of a stride, the alignment of hips and shoulders, the company of companions walking across the same stretch of ground. Between 1.5 million years ago and 1 million years ago, along the shores of what are now northern Kenyan lakes, a series of footprints left by early Homo provide one of the rarest and most intimate records of our past. The reveal begins with the Illiret footprints, discovered along the eastern edge of Lake Turkana. These impressions are remarkable, not because they are the first hominin footprints ever found. That honour belongs to the much older Laetoli prints of Australopithecus afarensis, dating to over 3.5 million years ago, but because they belong to bodies that already look much more like our own. Preserved in fine mud and ash layers dated to about 1.5 million years ago, they show feet with arches, aligned big toes, and stride lengths comparable to those of modern humans. These are not the flat, curved-toed prints of apes or australopiths. They are the steps of Homo erectus, a species whose legs and pelvis had already adapted for long-distance walking. The information encoded in these tracks is richer than one might expect from shallow impressions in ancient mud. Careful analysis of depth, shape and spacing allows researchers to reconstruct gait. The Illiret prints show a striding biped with heel strike at the back, toe off at the front, and an efficient transfer of weight across the arch. The feet are narrower than those of Australopiths, with a toe alignment that suggests stability and speed. Stride length indicates individuals similar in height to modern humans, some approaching 1 metre 70 centimetres tall. These were not shambling walkers, they were long-legged striders capable of covering ground efficiently. Even more evocative is what the groupings of footprints reveal. At Illiret, multiple sets of tracks run parallel to each other, suggesting that individuals walk together across a mudflat. This is not a single person wandering alone, but a group moving in the same direction at the same time. Some prints are larger, others smaller, hinting at a mix of adults and subadults. The spacing of tracks suggests coordinated movement rather than scattered randomness. It is one of the earliest pieces of evidence for hominins travelling in groups on open ground, leaving behind not only the shape of their feet, but also the suggestion of social bonds. Cubiphora, further to the north along the same Great Lake, preserves another set of footprints from roughly the same time. These two belong to Homo erectus and show the same hallmarks of modern locomotion. Their preservation in volcanic sediments has allowed detailed study, confirming that by this period our ancestors were already fully committed to striding bipedalism. The long arch, the narrow heel, the forward-facing big toe, all combine to show that walking as we know it today was already well established by 1.5 million years ago. Running, too, becomes a possibility, as the anatomy of the print suggests elastic recoil in the foot that would have aided endurance. What makes footprints such a unique record is their immediacy. Bones may tell us about individuals who died, and tools tell us about moments of activity, but footprints are moments of life. They capture a day when the ground was wet, when a group of hominins crossed a muddy surface, leaving behind transient impressions that only geological accident preserved. They do not show us hunting or tool-making or fire. They show us something more ordinary yet more profound. People walking together. That ordinariness is exactly what makes them powerful. It is the closest we come to time travel to walking beside them. The broader implications are significant. Efficient bipedal walking and possible endurance running would have expanded the range of Homo erectus. They could travel between water sources, follow migrating herds, and explore new territories. The group movement suggested by parallel tracks indicates coordination, perhaps even planned travel. To walk in a line is to follow a leader, or to keep a formation, reducing exposure to predators. Such behaviour would have supported foraging, scavenging, and migration. The footprints, in other words, are not just about anatomy but about ecology and society. We must, however, be humble about what we cannot know. The tracks do not tell us what the individuals were saying, if anything. They do not tell us whether they were hunting, gathering plants, or simply moving from one camp to another. They do not preserve faces or gestures or moods. All we have are shapes in mud, measured in millimetres but speaking across 1 million years. To interpret them requires caution, for each print is subject to erosion, distortion, and the chance of preservation. Yet across the multiple sites, the consistency of evidence builds confidence. These were humans in every anatomical sense, walking in ways we still recognise today. The haunting question is why such simple traces strike us so deeply. Perhaps it is because we too leave footprints when we walk along wet sand or mud. We know how fleeting they are, erased by wind or waves within hours. To find them frozen in time for over 1 million years is to be confronted with continuity. Someone walked there before us, someone with feet shaped like ours, someone who may have carried thoughts and plans, though unrecorded. They are gone, but their steps remain. And so, we find empathy not in bones or stones, but in the humble depressions of feet. They remind us that long before art, before firelight stories, before the carved hand axe, humans were already walking together. Were elephants and hippos the real teachers of patience? When we think of early humans, we often imagine them chasing antelope across open savannas or gathering roots in wooded patches. But from about 1 million years ago, 1,700,000 to 1 million years ago, the African landscape was dominated by animals of such size and presence that they must have dictated the rhythms of life for every predator, scavenger, and opportunist that shared the land. Elephants larger than today's species, hippos in enormous numbers, giant zebras and buffalo, even giraffids with horn shapes unlike anything alive now. These were the architects of ecosystems. For hominins like Homo erectus, the presence of megafauna meant opportunity and danger in equal measure. To approach a carcass of an elephant was to face a problem of scale. The reward was immense, hundreds of kilograms of meat, marrow, and fat. The risk was equally great, trampling by the living animal, or confrontation with lions, hyenas, and vultures already competing for the prize. The reveal comes from ecology. Large animals play a special role in ecosystems because their size slows down their metabolism and extends their lifespans. A giant elephant may live decades and reproduce slowly, but its death releases a bonanza of resources. The carcass of a single elephant could feed entire groups of hominins for weeks if they could gain access. Similarly, a hippo stuck in mud or felled near a riverbank provided an energy return unmatched by smaller prey. The challenge was timing. These animals did not die often, and when they did, their remains attracted carnivores and scavengers from kilometres away. To exploit megafauna, early humans had to master patience, waiting for opportunities, monitoring landscapes, and seizing moments when larger carnivores were absent. The information we have comes not only from bones with cut marks, but also from ecological modelling. Studies of energy returns suggest that scavenging from megafauna was one of the most profitable strategies available to hominins. Even if early humans were not the first to bring down a giant animal, the act of carving flesh from an elephant carcass or smashing open hippo bones for marrow provided far more calories than hunting smaller game. This does not mean that Homo erectus was passive. The ability to observe, anticipate, and intervene required intelligence, coordination, and courage. In a way, elephants and hippos became unwitting teachers. They taught humans to recognize opportunity, to share food in large groups, and to endure long stretches of scarcity punctuated by sudden abundance. Archaeological sites across East Africa preserve traces of these interactions. At some locales, entire bones of elephants show marks of stone tools, while others preserve fragmented hippo remains. These assemblages indicate repeated encounters with large animals. yet we should resist the temptation to see hominins as mighty hunters bringing down megafauna with ease. The evidence leans toward opportunism rather than dominance. It's more plausible that early humans learned to track the vulnerability of animals, exploiting droughts, river crossings, or natural accidents. In this sense, patience and opportunism were as important as strength or speed. The presence of megafauna also shaped the social behaviour of hominins. Large carcasses provided more food than a small group could consume before it spoiled. This encouraged sharing, whether willingly or under social pressure. The cooperative division of meat may have deep roots in these encounters. To butcher an elephant carcass efficiently required multiple hands. To defend the site from hyenas or lions required many eyes and strong coordination. In such contexts, patience was not just about waiting for opportunities, but about managing them once they arrived. The ecological lesson of megafauna is scale. To live alongside giants forced early humans to think on larger temporal and spatial scales. A herd of elephants could strip vegetation from a landscape, altering the distribution of plants and water. A dead hippo could alter predator movements for days. Hominins did not control these processes, but they learned to anticipate and exploit them. In this way, megafauna shaped the cognition of our ancestors as much as their tools did. We must also note that hominins were not alone in this niche. Carnivores like lions, leopards, and saber-toothed cats, as well as scavengers like hyenas, all competed for access to megafauna. The fossil record shows bite marks overlaid with cut marks, evidence of a sequence of access. Sometimes carnivores fed first, humans second, sometimes the reverse. The dance around carcasses was complex and dangerous. To learn patience in such a context was also to learn timing and caution, skills that may have been crucial for survival. As humble scientists, we admit we cannot reconstruct the full stories. We do not know if Homo erectus ever actively brought down elephants, though some argue they may have targeted young or weakened individuals. We do not know how they divided meat among group members or how they negotiated with other scavengers. What we do know is that bones carry both tooth marks and stone-cut marks, testimony that hominins were present at the table of giants. The haunting question remains, were elephants and hippos the silent partners in our evolution? By forcing us to wait, to observe, to act in coordinated bursts, did they shape our patience, our cooperation, and even our sense of time? Perhaps the rhythm of scarcity and abundance imposed by megafauna trained human groups in endurance and sharing. If so, the giants did more than feed us. They taught us how to be human. To flow into the presence of giants, it helps to step back and picture the landscapes our ancestors walked. From the Rift Valley of East Africa to the grasslands of southern regions, the terrain was not empty savanna but a patchwork of lake shores, open plains, gallery forests and marshy riverbanks. These mosaics of habitat were magnets for herds of large herbivores, just as Serengeti plains attract wildlife today. The scale, however, was amplified. Elephants with longer tusks and larger bodies than any living species browsed and trampled their way across the vegetation. Hippos crowded river mouths in densities that would be almost unimaginable now. Alongside them roamed giant zebra, buffalo the size of small trucks, and giraffids with extravagant horns. To exist in this world was to live in constant proximity to bulk and power. For hominins, the daily act of scanning the horizon must have been framed by these animals. To see elephants moving across the distance was not simply to witness a spectacle, but to be presented with both a challenge and a possibility. If the animals were healthy, they were untouchable, but if one faltered, fell into mud, or died of natural causes, the landscape itself seemed to transform. Scavengers circled, vultures marked the sky, and the smell of opportunity travelled on the wind. The decision of whether to approach required judgment. Would lions be driven off, or would they fight back? Could hyenas be distracted long enough to slice meat from a limb? The choice demanded more than brute strength. It required patience, calculation, and the kind of social negotiation that comes only when survival depends on cooperation. It is in this setting, dense with bodies far larger than ours, that the story of Homo erectus and its relatives unfolded. The giants were not background, they were the stage itself. What mattered more, food or where to drink it? For a long time, researchers imagined that early humans were shaped mainly by the search for calories, for protein, for the chase of animals or the digging of tubers. Yet as work across the East African Rift has shown, the true limiting factor for survival between 1.5 million years ago and 1 million years ago may have been water. Without regular access to fresh water, no amount of meat or plant food mattered. The Rift Valley, stretching like a scar across eastern Africa, was not a stable or predictable environment. Its lakes swelled and shrank, sometimes vanishing altogether, sometimes spreading into vast inland seas. To follow these water shifts is to follow the pulse of human evolution. The reveal begins with geology. The East African Rift is a tectonic system pulling the continent apart, creating fault lines and basins that fill with water when climate allows. In periods of high rainfall, deep lakes expanded across the rift floor. In drier periods, the same basins contracted into shallow saline pools or dried into dust. Evidence from drill cores taken at sites like Lake Turkana and Olduvai Gorge shows repeating patterns of lake expansion and collapse across this time span. These were not slow changes, but sometimes rapid oscillations tied to glacial-interglacial cycles. A freshwater lake could support fish, mollusks, hippos, crocodiles, and lush vegetation along its shore. A dry basin, by contrast, forced hominins to move, to adapt, or to die. The information preserved in sediments tells us that Homo erectus and Paranthropus lived through precisely these fluctuations. At Olduvai, beds dating from around 1.2 million years ago show layers of diatomite indicating the presence of a deep freshwater lake, alternating with sandy layers marking dry conditions. Fossil assemblages mirror these shifts. Hippos and aquatic birds appear in wetter phases, while grazing antelope dominate drier horizons. The rhythm of water and absence of water structured which animals were available to hunt or scavenge, and which plants could be gathered along the margins. For hominins, the challenge was not only food supply, but hydration itself. A large-bodied mammal like Homo erectus required significant water intake to sustain long treks in open landscapes. Access to freshwater lakes and rivers was thus a matter of physiological necessity. Sites near ancient shorelines may reflect this dependency. It is not coincidence that so many Acheulean handaxes are found close to paleo lakes. Stone tools cluster where water once pooled, suggesting that human activity concentrated around these critical nodes. Paranthropus, with its specialized jaws and heavy chewing muscles, faced the same constraint. Even if its diet relied heavily on tough vegetation, it still needed access to fresh water. Stable isotope studies show C4 plant consumption, but without lakes or rivers, those resources would have been harder to process or less available. In this sense, the survival of Paranthropus was just as bound to rift hydrology as that of Homo erectus. The broader ecological implications are striking. Rift hydrology was unstable not only on seasonal timescales but across centuries and millennia. Lakes could swing from fresh to saline within decades. Shorelines could retreat by kilometers in a generation. For hominins, such instability demanded mobility. Groups had to monitor changing water bodies and anticipate where the next reliable source would be. This mobility is reflected in the wide distribution of Homo erectus fossils across the Rift Valley. The species was not sedentary, but capable of tracking water through shifting landscapes. We should be cautious, however, in drawing straight lines from geology to behaviour. Humans did not have weather satellites or hydrological models. Their knowledge of water came from direct experience, from memory of past journeys, from social transmission of where to go when rivers dried. The traces we see in sediments are the backdrop, not the lived knowledge of the people themselves. Yet even so, the geological record reminds us that survival was often about timing and placement. To be in the right place when water returned could mean abundance. To be caught when lakes receded could mean crisis. One haunting question remains. Was it food or water that set the real limits on human expansion? If Homo erectus could butcher hippos and elephants, it had solved part of the nutritional puzzle. But without reliable water, no hunting skill could compensate. In this light, our ancestors may have been less hunters of animals and more followers of lakes. The story of humanity between 1.5 and 1 million years ago might best be read not as a tale of tools and meat, but as a story of hydrology, of moving with the breath of water across a restless rift. When we follow the thread of water further, we begin to see how it might have influenced not only survival, but also the rhythms of daily life. Imagine early Homo erectus at the edge of a Rift Valley lake around 1,200,000 years ago. Dawn breaks, hippos bellow in the shallows, and birds scatter across the reeds. The lake is both larder and lifeline. Fish swim beneath the surface, mollusks cling to mudflats, and crocodiles lurk nearby. Such an environment provided not only hydration, but a predictable meeting ground where prey animals gathered to drink. For hominins, a lake edge was a supermarket, water fountain, and ambush corridor rolled into one. But the reliability of that lake could never be assumed. Archaeological layers show abrupt transitions, sometimes only a few centimetres apart in sediment but representing profound ecological change. A shoreline that once supported hippos could dry to cracked mud within a human lifetime. This volatility demanded foresight. Groups who remembered that another valley to the north held water when their own basin failed would have held a crucial advantage. It is tempting to imagine that some of the earlier strands of long-term memory and social teaching, stories of where to go when the land turned harsh, emerge from precisely this need to track the wandering of water. The distribution of Acheulean tools reinforces this picture. At 𝐓𝐈𝐌𝐿𝐄𝐒𝐒, 𝐓𝐈𝐌𝐿𝐿𝐄𝐒𝐒 and 𝐓𝐈𝐌𝐿𝐿𝐄𝐒 stone tool scatters are often found in contexts linked to ancient lake margins. It suggests that napping was not random but tied to the places where groups congregated. When water collected, people lingered. They may have retooled, butchered animals that came to drink, or waited for opportunities to scavenge. The clustering of artifacts is not just an accident of preservation, but a reflection of the centrality of hydrology to hominin life. Even the physiology of Homo erectus speaks to this tethering. A large brain demands constant hydration, and unlike many mammals, humans cannot easily tolerate dehydration. Sweat cooling allows long-distance walking and running, but it makes water loss significant. This trade-off means that Homo erectus was evolutionarily committed to living within reach of reliable water. Their very biology, in other words, was shaped by the lakes and rivers of the rift. Water did not only dictate where hominins could survive, but also where ecosystems could flourish. A full lake drew herds of herbivores, and herbivores drew carnivores. To follow water was to follow life itself. And perhaps this is the deeper lesson, that before tools, before fire, before art, the first great map our ancestors carried was one of rivers and lakes, inscribed not on stone or hide but in memory and movement. The real frontier was always the shoreline. Why did Homo erectus brains get bigger when diets got harsher? The question forces us to look past the convenient story of smooth progress, the tidy narrative in which new species appear. Brains expand and intelligence rises in step with comfort. The truth of the period between about 1,600,000 years ago and 900,000 years ago is far messier. This was not a time of stability or plenty. Climate oscillations began to intensify as the mid-Pleistocene transition gathered pace. Ecosystems grew more volatile, and food webs shifted in unpredictable ways. Yet amid these challenges, Homo erectus cranial capacity increased, marking a long, slow climb that would eventually bring human ancestors to levels far beyond any other primate. The paradox is that the brain, our most energy-hungry organ, grew larger precisely as survival became more precarious. The reveal begins with the numbers, or rather, the shapes behind them. Fossil skulls from sites like Dmanisi, Sangiran, and East Africa show that the earliest Homo erectus had cranial capacities of around 600 to 800 cubic centimetres, larger than Australopiths, but still closer to chimpanzees than to us. By the time we reach specimens from just over 1 million years ago, some individuals crossed the 1,000 cubic centimetre threshold. This did not happen suddenly, but as a gradual swelling over hundreds of thousands of years, with variation across populations. The trend, however, is undeniable. Brain size was on the rise during one of the most turbulent phases of Earth's climate. The information from physiology tells us why this matters. Brains are expensive organs. In humans today, they consume about 20% of our resting metabolic energy, even though they account for only about 2% of body weight. For Homo erectus, enlarging the brain meant paying an even steeper daily energy bill in a world where calories were not guaranteed. How could such a trade-off succeed? One answer lies in meat. As butchery evidence from across East Africa shows, early Homo had primary access to animal carcasses, and marrow extraction became a consistent practice. Meat and fat are calorie-dense, easily absorbed fuels compared to raw plant material. Access to large mammals may have underwritten the brain's expansion, even if hunting remained risky and scavenging often opportunistic. But energy alone cannot explain the puzzle. Ecological pressures likely pushed the brain to grow in ways that were not purely nutritional. The volatility of the Rift Valley landscape, with its shifting lakes and grasslands, forced groups to move, to anticipate, and to adapt quickly. A larger brain may have been useful not just as a hungry organ, but as a flexible problem-solving machine, capable of dealing with a novelty. The unpredictability of water sources, the danger of predators around carcasses, and the complexity of coordinating group activities all would have favoured individuals who could process information more efficiently. In this light, the brain's expansion looks less like a luxury and more like an adaptation to chaos. Another factor may have been the social environment. Larger carcasses provided more food than a small group could consume immediately. This abundance demanded cooperation, whether to share meat, defend it from carnivores, or process it before it spoiled. Social coordination at this scale requires memory, recognition of individuals, and perhaps even the beginnings of more structured teaching. While we cannot claim the origins of language or symbolism here, the steady increase in brain size may reflect the cognitive load of living in larger, more complex groups tied together by cooperation around food. It is also worth noting what the fossil record shows about variation. Not every Homo erectus skull shows dramatic expansion, and some individuals remained within the lower range for hundreds of thousands of years. This unevenness reminds us that evolution is not a ladder, but a branching, messy process. Some populations may have grown brains faster than others, depending on local ecological pressures and resource bases. The shared trend across continents, however, suggests that the pressures toward brain expansion were widespread, not confined to a single region. As humble scientists, we should be careful not to overstate our knowledge. We cannot measure thought from fossil bone, and we cannot reconstruct the daily challenges faced by a hominin family on a dry plain. What we can say is that the coincidence of brain expansion, dietary reliance on meat, and ecological volatility is striking. It suggests that intelligence did not evolve in comfort, but in adversity, that the brain did not grow because life was easy, but because it was hard. The haunting question, then, is whether our species owes its defining organ to a period of scarcity rather than abundance. Did brains grow precisely because survival was difficult, forcing our ancestors to innovate, cooperate, and endure? If so, the great irony of human evolution is that the very organ we use to imagine a world of security and stability was forged in landscapes where neither existed. One further angle is metabolism itself. Scholars have suggested what is sometimes called the expensive tissue hypothesis. In essence, if one organ grows more costly, another must shrink or become more efficient. In the case of Homo erectus, this may have meant a reduction in gut size. A shorter digestive tract is less able to process bulky, fibrous plant foods, but more efficient with high-quality animal protein and fat. This physiological rebalancing would have locked the species into a path where meat became more than a supplement. It became a central part of the diet. The consequence was that Homo erectus was tethered to strategies of butchery, scavenging, and hunting that could support a larger brain. We cannot see the intestines in fossils, but the shape of the ribcage and pelvis hints at changes in body form consistent with this trade-off. Another thread is the relation between endurance and cognition. A body capable of long-distance walking and running could range widely in search of food and water. Yet such journeys demanded planning. You had to know where waterholes were, how long it would take to reach them, and whether resources would still be present on arrival. This is not the kind of decision-making one can leave to chance. The interplay between physical endurance and mental anticipation may have driven further gains in brain function. The landscape itself became a cognitive map, rewarding those who could remember routes and times with survival. We must also consider predators. Lions, saber-toothed cats, hyenas, and crocodiles posed constant threats. Extracting marrow from a carcass required not just tools but vigilance. A larger brain could manage the simultaneous tasks of cutting, watching, and coordinating escape. Survival meant balancing opportunity with risk, and that balancing act was likely a crucible for sharper minds. The paradox remains fascinating. While the climate system destabilized, while lakes dried and grasslands contracted, Homo erectus grew a bigger brain. It is tempting to see this not as contradiction, but as cause. Perhaps intelligence did not thrive in spite of harshness, but because of it. If that is the case, then the very organ we use to tell stories, to imagine, to wonder about deep time, is a monument to endurance under pressure. And that leads us to wonder, is the human brain, even today, still best at solving problems born of scarcity rather than abundance? That haunting question lingers every time we look at the long, slow swelling of skulls in the record of Homo erectus. What if Homo erectus was not one neat species but more of a family reunion, scattered across continents, carrying a shared name but diverging in form and behaviour? To ask this is to unsettle the old picture of a single, tidy lineage striding out of Africa and settling the old world in uniform fashion. The fossils suggest a messier story, one in which early Homo looked different depending on where you find them, adapted to local conditions, and perhaps even lived as partially isolated populations for long stretches of time. Between about 1,800,000 years ago and 1 million years ago, what we call Homo erectus was anything but monolithic. The reveal begins in Georgia, at the site of Dmanisi. Discovered in the late 20th century, this collection of skulls and bones forced paleoanthropologists to rethink the neat categories of species. Here, in sediments about 1,800,000 years old, were multiple individuals with strikingly different appearances. One had a long, narrow brain case and small face. Another had a more robust jaw and larger brow ridges. The brain sizes ranged from less than 600 cubic centimetres to over 750. Yet they were all found in the same place and dated to the same horizon. The simplest explanation is that they belonged to a single population showing remarkable variation. If true, then the early dispersal of Homo out of Africa carried with it not a polished, uniform type, but a flexible, diverse set of bodies and faces. Asia adds another layer to the puzzle. In Java, fossils attributed to Homo erectus show features distinct from African specimens. The cranial vaults are thicker, the brow ridges more massive, and the faces more retreating. These fossils span a wide period, from over 1 million years ago down to perhaps 100,000 years ago, suggesting that an Asian branch of Homo erectus persisted long after African populations had shifted toward new forms. China tells a similar story. At sites like Zhoukoudian, fossils dated to several 100,000 years ago reveal yet another blend of traits. Large brain cases in some, but heavy brow ridges and angled vaults in others. These differences raise the question, are we looking at one species spread thin across continents, or a patchwork of related lineages that shared an origin but diverged as they adapted to local conditions? In Africa, meanwhile, Homo erectus, sometimes called Homo ergaster in this context, retained its own character. Fossils like the famous Turkana boy from Kenya, about 1,500,000 years old, show a tall, slender body, adapted for heat dissipation on open savannas. The cranial form is lighter than many of the Asian examples, with thinner bone walls and a less pronounced brow ridge. Some scholars argue this justifies the label Homo ergaster, reserving Homo erectus for the thicker-skulled Asian forms. Others see the distinction as unnecessary, preferring to view the differences as regional variation within a single adaptable species. The information these fossils give us is not just about anatomy, but about dispersal. For Homo erectus to appear in Georgia, Indonesia and East Asia by 1,500,000 years ago, they must have moved quickly out of Africa after their first emergence. That movement was not a single event, but a series of dispersals, some reaching further than others, some perhaps leaving small populations stranded at the edges of habitable land. Isolation, combined with the local ecology, would have sculpted their skulls and bodies in different ways. A group living in tropical Southeast Asia faced different challenges from one living on the windswept plains of East Africa. Diet, climate and predators all shaped their forms. What remains uncertain is how connected these populations remained. Did individuals ever move back and forth between Africa and Asia, mixing genes and keeping the species coherent? Or did the distances, deserts and mountains create long-lasting separations? The fossil record is too thin to give us definitive answers. We can only infer from the fragments that Homo erectus was a species in motion, stretching its range, experimenting with form, and leaving behind a legacy of diversity that complicates any attempt at simple classification. The resolution of this story is not tidy. To label all these fossils Homo erectus is to use a convenient shorthand, a box that holds many shapes. But the haunting question is whether the box hides more than it reveals. Were we dealing with one species, or a family reunion of related but distinct populations, cousins more than siblings who shared experiments in survival, wrote the first truly global chapter of our genus? The evidence so far suggests that humanity's first world travellers were also humanity's first lesson in variation. That even in deep time, there was never just one way to be human. One way to appreciate the diversity within what we call Homo erectus is to look at the scale of time involved. This species, or collection of populations, endured for more than 1.5 million years. That is a span longer than our own species has yet existed. Over such a stretch of time, through shifting climates and continents, it would be remarkable if bodies had remained static. The very longevity of Homo erectus may explain why it looks so different in different places. The bones we find in Indonesia from a few 100,000 years ago were not the same individuals who left Africa almost 2 million years earlier. They were descendants of descendants, shaped by countless generations of adaptation. It is easy to forget that evolution does not pause just because we assign a single name to a group of fossils. Another point is that Homo erectus is the first hominin to occupy such an enormous geographic range. Earlier species of Homo, such as Homo habilis, remained largely confined to Africa. Homo erectus crossed barriers, reached temperate zones, and ventured into regions with new plants and animals. This broad ecological spread alone would have promoted variation. Just as wolves in the Arctic look different from wolves in India, we might expect Homo erectus in Java to differ from Homo erectus in Kenya. Some of those differences may have been superficial, but others ran deeper, affecting skull structure, body proportions, and even brain growth trajectories. At the heart of the debate is whether we should split or lump. The splitters argue that African specimens deserve the separate name Homo ergaster, distinguished by a lighter cranial construction and often associated with the earliest Acheulean tools. The lumpers argue that such differences are minor compared to the similarities, and that Homo erectus, whether in Georgia, China or East Africa, was one adaptable species. Both positions carry risks. If we split too finely, we create species where there may only have been local populations. If we lump too much, we smooth over real diversity that mattered for survival. The truth may lie in the middle. Homo erectus was a single lineage with many regional branches, some of which may have been as distinct as subspecies are in modern animals. The fossils themselves remind us how incomplete the record is. For every skull or jaw we hold in a museum, there are likely thousands that never fossilized or that remain buried. The variation we see might be only a fraction of the true diversity. This incompleteness fuels debate. Some scholars emphasize the Dmanisi fossils as proof of variation within one group, while others highlight the persistent differences between Africa and Asia as evidence of deeper splits. Without DNA, which does not survive at these ages in tropical environments, we are left to interpret bones and stone tools, and to admit that certainty will remain elusive. Still, the implications are profound. If Homo erectus was indeed a single species spanning Africa and Asia, then it represents an extraordinary capacity for flexibility, able to thrive in deserts, forests and coastlines alike. If instead it was a network of related populations, then the story becomes one of parallel experiments, each adapting to its own conditions, some succeeding for hundreds of thousands of years, others fading away. Either scenario marks a turning point in human evolution, the moment our genus became global. The haunting question that follows is whether we, as modern humans, are heirs to one of those regional branches or to the whole tapestry. When we say Homo erectus, are we invoking a single ancestor or a chorus of ancestors, some of whose voices are forever lost? This ambiguity is not a weakness of science, but a reminder of how much we do not know. Our task is to keep piecing together the fragments, accepting that the family reunion may never be neatly sorted, and that the very messiness of Homo erectus might be the truest picture of what it means to be human. To look at a block of stone and see a shape that does not yet exist is one of the quiet revolutions in human history. Between about 1,200,000 years ago and 800,000 years ago, the stone tools of our ancestors began to show a refinement that earlier generations had not attempted. The rough and heavy picks of the earliest Acheulean gave way to thinner, more symmetrical handaxes, their edges carefully thinned, their outlines approaching balance in 2 and even 3 dimensions. To reach that level of craftsmanship meant more than hitting rock with rock. It meant imagining a final form, holding it in the mind, and then removing flakes in sequence until the invisible shape became real. This was not invention in the sudden sense we like to attribute to geniuses, but slow, cumulative change, yet no less profound for its gradualness. The reveal of this story is found in sites like Khonso in Ethiopia, and later deposits across East Africa and beyond. At around 1,600,000 years ago, handaxes were still thick and clumsy. By 1,200,000 years ago, however, they began to show consistent thinning, straighter edges, and tips shaped with more precision. This was not an isolated act by one skilled napper, but a widespread trend seen in multiple regions. The inference is that techniques were being shared, passed down, and gradually improved upon across generations. Unlike older one flakes, which could be produced with a few strikes and required little forward planning, these new handaxes demanded a vision of symmetry and a practiced sequence of blows. The information locked in these stones tells us something crucial about cognition. To impose symmetry on a natural object requires both abstraction and control. The napper had to know what not to hit, as much as what to hit. They had to see a line of balance where no line existed, a mental axis running down the tool, and then shape each side to mirror the other. Modern experiments in napping suggest that such skills are not easily learned by imitation alone. Verbal teaching is not required, but demonstration, repetition, and correction are. It implies that learning itself had become a structured process. Communities must have valued these skills, with elders or experienced toolmakers teaching the young. The refinement of handaxes was not only a technological milestone, but a social one. The implications stretch further. A refined handaxe is more efficient. It slices longer, resists breakage, and can be resharpened multiple times. It also represents economy of effort. A single well-made tool could serve many purposes, from butchering animals to woodworking. But function may not tell the whole story. The consistency of shapes across wide areas hints at a sense of tradition, perhaps even style. Some archaeologists have wondered whether the symmetry itself carried a symbolic weight, though we must be cautious not to project modern aesthetics onto ancient minds. What we can say is that symmetry required foresight, and foresight is a cognitive leap. By 800,000 years ago, some handaxes achieved what scholars call three-dimensional symmetry, where not only the outline but the cross-section was balanced. To do this required thinning the core by striking away large flakes with precision, often using softer hammerstones like bone or antler to control the blows. This was difficult even for skilled modern nappers who try to replicate the process. The persistence of such tools suggests that communities invested significant time in training, and that younger individuals must have spent years practicing before they mastered the technique. This reveals an ancient patience, an investment in learning that echoes across 1,000,000 years. The resolution, then, is not only about tools but about minds. The handaxe that is symmetrical is also a mirror, reflecting the growing ability of humans to imagine what is not yet real, and then bring it into being. That ability would later underpin language, art, and architecture. At this stage it was still silent, unadorned, and functional. But the haunting question lingers. When an early Homo erectus or Homo ergastus sat with a stone, chipping away to reveal a form in their head, did they feel pride in the symmetry they produced? Did they notice beauty and balance long before they could speak of it? We cannot know, but the stones whisper that something within us was beginning to awaken. When we think of these early handaxes, it is tempting to view them only as artifacts, stone objects that survive while everything else, wood, sinew, language, has vanished. But to the people who made them, these tools were more than stone. They were extensions of the hand, bridges between thought and matter. Each flake struck from a core was a small act of intention. To pursue symmetry meant choosing not the easiest path, but the one that required patience, correction, and a mental image that could guide the process. That pursuit of symmetry may have been the first time humans sought to impose order on the randomness of nature. It is worth reflecting on how difficult this skill is to learn. Modern experimental knappers often need years of practice before they can thin a hand axe to true symmetry without breaking it. The ancient makers had no textbooks, no diagrams, only observation, demonstration, and their own hands. This suggests that communities had structured ways of transmitting knowledge, even if they lacked words as we know them. Watching an elder imitating, failing, and trying again would have been part of daily life. That act of patient practice is perhaps the deepest root of culture. A tradition of making was being born, not in a sudden leap but in the quiet rhythm of flake after flake. The refinement also signals something about perception. To recognize symmetry is to notice balance. Many animals respond to symmetry in mates or in natural shapes, but here it was deliberately created. Once the mental template existed, it could be applied again and again, across generations and across continents. The same basic shapes turn up in Africa, in Europe, and in Asia, testifying to a shared way of seeing. Some anthropologists have argued that this shared vision represents not only function, but also an early form of aesthetic judgment. It may not have been art, but it was art's ancestor, the idea that form matters beyond pure utility. There is also the question of time. Making a refined hand axe was not quick. It took far more time than striking a few flakes off a core. This investment suggests that the value of the tool outweighed the effort. It may have been used for long periods, resharpened and carried from place to place. In that sense, a good hand axe was a companion object, a trusted resource that travelled with its maker. Some were abandoned, others lost, but many show signs of long use. The act of investing hours in a single tool hints that these humans were planning not only for today but for tomorrow. They had moved from immediate need to future orientation, even if only in small increments. From a cognitive perspective, the leap to three-dimensional symmetry is especially significant. It required rotating the object mentally, striking flakes not just on the flat surface but along the edges and curves, adjusting angles to maintain balance. This spatial reasoning foreshadows later achievements in construction, navigation, and even symbolic systems. A brain capable of this kind of visualization was becoming a brain capable of far more than survival. Yet we should remain humble. These were not modern humans, and we cannot project modern imagination back onto them. They were shaping tools, not painting caves. Still, in the slow precision of their work we glimpse the deep roots of abilities that would one day allow us to build cities and spacecraft. There is also the social dimension. If younger members of a group practiced toolmaking, their mistakes would have produced piles of broken or poorly shaped pieces. Archaeologists often find such scatterings at sites, alongside the finely crafted hand axes. This suggests that learning was visible, perhaps even encouraged within the community. A young napper's errors may have been tolerated, just as we tolerate the scribbles of children today. This tolerance is no small thing. It means that time and resources were devoted to teaching, rather than spent only on immediate survival. That investment in the next generation is the essence of culture. It is striking, too, how conservative the Acheulean tradition was. For hundreds of thousands of years, the hand axe remained a central tool, with slow refinements, but no sudden revolutions. In an age where we measure innovation by decades, this patience feels alien. Yet perhaps it speaks to a different rhythm of life, where stability was more valuable than novelty. The constancy of the Acheulean suggests that once a community had mastered symmetry and thinning, the tool met their needs so well that little change was required. Evolutionary success is not always about rapid innovation. Sometimes it is about perfecting a form so deeply that it endures almost unchanged for geological spans of time. And yet, the hand axes are not identical. Regional styles emerge, subtle differences in shape and flaking patterns that suggest local traditions. These regional signatures may be the first whispers of cultural identity, ways of making that distinguished one group from another. The differences are not dramatic, but they matter. They hint that even at this early stage, humans were not a single uniform population, but a patchwork of groups with their own habits, preferences, and perhaps senses of belonging. When we hold one of these handaxes today, it can be difficult not to see it as beautiful. The balance of its edges, the feel of it in the hand, the sharpness of its lines all resonate with our own sense of form. But we should remind ourselves that beauty was not necessarily the maker's goal. Efficiency, durability, and sharpness were likely at the heart of the design. Yet in reaching for function, they also stumbled upon form. Perhaps that is how much of human creativity has always worked, solving practical problems in ways that unexpectedly give rise to art. The haunting question that lingers is whether those early humans noticed what they had done. Did they admire their own work, or simply see it as a tool? Did they feel satisfaction in the symmetry itself, or only in the cut it delivered? We cannot know, and perhaps that uncertainty is part of the story. The stones remain silent, but they whisper of minds that were changing inch by inch, flake by flake, towards something that would one day become us. What the refinement of the Acheulean handaxe truly represents is not a single breakthrough, but a slow, patient deepening of human capacities. To envision, to plan, to teach, to value balance, and to invest in tomorrow. These qualities may not have been conscious in the way we experience them now, but they were present in embryo, carried in the rhythm of striking stone. And in that rhythm, over hundreds of thousands of years, humanity learned the power of symmetry, an idea so simple yet so profound that it has never left us. Can you find home in a pile of stones? That is the question that archaeologists wrestle with when they kneel in ancient dust and trace the scatter of flakes, bones and ash left behind by hominins over 1 million years ago. No roof beams survive, no walls, no bedding of grass or furs. Yet here and there, at sites stretching from the Rift Valley to South Africa, hints appear that early humans were not merely passing through landscapes, but pausing, settling, and shaping small pockets of order in a harsh world. Between about 1.5 million years ago and 1 million years ago, we glimpsed the beginnings of site organisation. Clusters of stone tools, repeated use of certain spots, sometimes even traces of fire. They are faint shadows of home, and while we must be careful not to project too much onto them, they allow us to imagine what it meant to carve out a place of belonging long before the first houses. The reveal begins with Olduvai Gorge, that deep wound in the earth where time has layered itself into beds of sediment like the chapters of a book. In beds 2 and 3, sites such as 𝐓𝐿K West and JK2 preserve concentrations of stone tools mixed with butchered animal bones. These are not random scatterings carried by floods. They show deliberate accumulation, with cut marks on bone surfaces aligned with tools nearby. The clustering suggests that groups of Homo erectus were repeatedly returning to the same locations to process carcasses, perhaps because the terrain offered a reliable water source or shade from acacias. The arrangement of materials tells us that these were not just kill sites, but temporary activity spaces, where a group sat, worked, and likely rested together. A circle of tools may not sound like much, but in the language of deep time it is a sketch of community. The information becomes clearer when we look at sites beyond Africa. At Gesher Beno Yaakov in the Jordan Valley, slightly younger than our window but relevant, layers preserve stone tools arranged around patches of burned flint. The interpretation is controversial, but many scholars believe it shows repeated fire use and a degree of spatial organisation. One area for flaking stone, another for processing plants or fish. If this is correct, it suggests that by around 800,000 years ago, hominins were not just opportunistically occupying space, but actively dividing it into functional zones. This ability to structure activity spatially is one of the foundations of what we later call a living site, and it likely began earlier, during the period we are focusing on. Closer to 1.5 million years ago in East Africa, we see more subtle hints. At Kubifora in Kenya, some localities show clusters of flakes that seem to represent workshops. The refitting of flakes back onto cores, painstakingly done by archaeologists, reveals that stones were napped in one place rather than scattered across the landscape. Imagine an individual sitting with a cobble, striking it repeatedly and leaving behind the waste. Around them, others might have been butchering, resting, or even dozing. These concentrations suggest repeated choices about where to sit and work, choices that echo faintly as site organisation. The lack of preserved shelters makes it harder to push the evidence further. Wood, hides, and grasses vanish with time, leaving only indirect signals. Yet experimental work with modern hunter-gatherers shows that even ephemeral shelters, branches leaned together, skins stretched over poles, can leave patterns in the ground if reused. At sites like Acheulean in Kenya, archaeologists have found spatially consistent distributions of artifacts across multiple layers, hinting that groups may have returned season after season to the same locales. The predictability of rivers and resource patches likely anchored these places in memory. To call them home bases may be an exaggeration, but they were more than anonymous spots on a map. What resolution can we draw from such faint signals? Perhaps the haunting question is whether home began not with walls but with routine. If a group of Homo erectus sat together at dusk, sharing marrow scraped from bones, children mimicking stone strikes while adults sharpened tools, and all of them sleeping close to one another under the stars, was that not already home in its most ancient form? A pile of stones and bones might seem meagre to us, but to them it may have been enough. A place to return, a place to feel safe for a night or two, a place where the continuity of the group was reinforced. It reminds us that the beginnings of home are not architectural but social. They are the echoes of where people gathered, worked, rested, and, for a little while, lived together. And in that sense, even the scattered sites of 1.5 to 1 million years ago are not just traces of activity, but the first surviving footprints of humanity's oldest yearning, to belong somewhere, even if only for the length of a fire's glow. If we lean a little closer to the ground and look at the evidence with patience, what emerges is not permanence, but rhythm. Archaeologists often describe the repeated use of certain landscapes as persistent places. These are not towns or villages, but favoured spots returned to again and again. Around 1.5 million years ago, such persistence begins to show up faintly in the record. A river bend with reliable water, a ridge with stones suitable for napping, a clearing where prey were known to pass. These places drew groups back season after season. The sites may look different today, but the choices reveal minds that recognised patterns in a shifting world. Recognising a pattern, then acting on it, is one of the deepest roots of what we later call settlement. At Acheulean in southern Kenya, for instance, archaeologists have uncovered layers upon layers of Acheulean tools, not piled randomly, but spread across ancient lake margins that once pulsed with water. These deposits, stacked over hundreds of thousands of years, speak of repeated gatherings. Groups likely paused here to process carcasses, crack bones, and rest. The flakes left behind form halos around large handaxes, suggesting moments when individuals sat together to nap or resharpen. This is not simply subsistence, but also choreography, a shared use of space that required tolerance and cooperation. Even if no huts or circles of posts remain, the material speaks of habit. Elsewhere, in the South African cave of Wonderwerk, where traces of early burning have been identified, we also see hints of structured use. The artefacts are not evenly scattered, but tend to cluster, as if work was carried out in specific areas, while other areas may have been reserved for resting or tending a flame. Whether or not we can call these rooms is debatable, but the implication is that the cave was not just a hollow, but a lived-in space. It offered protection from weather and predators, and once groups discovered its safety, they may have returned for generations. Such places force us to rethink what home might mean. Today we think of 4 walls, a hearth, a bed. For early Homo, it may have meant something far simpler, the repeated act of stopping, gathering, and arranging activities in ways that felt familiar. Even without permanent structures, routine builds attachment. A clearing on a riverbank might have been remembered as where elders taught toolmaking, or where a child first gnawed marrow from a bone. When they returned the following year, the familiarity of the landscape may have evoked memory, turning wilderness into something more than wilderness. There is also the question of safety. To sleep in a cluster close to others is to gain protection. Predators are less bold against groups. Perhaps the circle of bodies at night was as important as any fire or tool. Archaeologists can see this indirectly. Concentrations of bones from multiple individuals of prey animals combined with tools and hearth traces suggest that many hands were at work. It is not proof of shared sleep, but it is difficult to imagine these sites without imagining the nights that followed the day's labour. The absence of shelters in the record does not mean they were absent in life. Even chimpanzees construct nightly nests and gorillas fashion leaf platforms. It is hard to believe that Homo, with hands already skilled in shaping stone, did not arrange branches or pile grasses for comfort. What would be left after 1,000,000 years? Almost nothing. Only the arrangement of stones, perhaps, or the repeated use of a hollow. Archaeologists sometimes look for phantom structures, subtle arcs of stone or post holes, but these are vanishingly rare. Still, the logic of survival suggests that even if perishable shelters do not survive, they must have existed in some form. And so we circle back to the haunting question, can a home exist without walls? The evidence suggests it can. Home may have been no more than a mental construct, a shared recognition that this is where we stay. That recognition, repeated and transmitted, seeded the human instinct for place that endures even now. When we look at the scatters of flakes at 𝐓𝐈𝐌𝐿, the clusters of bones at 𝐓𝐈𝐌𝐿𝐼, the darkened sediments of Wonderwerk, we are not just seeing the residue of subsistence. We are seeing the archaeology of pause, of routine, of belonging. It is fragile, but it is there. The record tells us that Homo erectus and its contemporaries were already transforming landscapes into familiar places, even if only for a season. That shift, from moving endlessly through a world to punctuating it with remembered sites, was the beginning of a story that will eventually lead to villages, cities, and nations. But at this early stage it was still quiet, still temporary, still measured in nights beneath the stars. The echoes that reach us are not architectural but behavioural, the faint but profound beginning of humanity's endless search for home. What happened to the ones who looked almost like us, but did not make it? This question hangs over the early Pleistocene like a shadow. Between about 1,300,000 years ago and 1,000,000 years ago, the evolutionary landscape was not empty of alternatives. Our ancestors, the tool-making, wide-ranging Homo erectus, were not alone. They shared their world with robust cousins like Paranthropus, with more delicate or fragmentary early Homo lineages that we still struggle to classify, and with species that may have represented experiments in adaptation that ended abruptly. The bones and teeth that remain are often incomplete, scattered, and rare. But together they hint at a broader diversity of hominins than we sometimes imagine. Survival was not inevitable, and the path that led to us could easily have looked very different had one of those other branches persisted. The reveal begins with Paranthropus boisei, often called the nutcracker man, because of its massive jaws and thick enamel teeth. By 1,000,000 years ago its days were numbered. Fossils at 𝐓𝐈𝐿𝐼 and 𝐶𝐻𝐿 suggest it still lingered into the early Middle Pleistocene, but soon after it vanishes from the record. Its specialisation on C4 plants, the grasses and sedges that once dominated East African landscapes, became a vulnerability when environments shifted and new grazers like antelopes and giant baboons pressed into the same niche. The very features that had made Paranthropus successful for nearly 1,000,000 years, the sagittal crest, the flaring cheekbones, the enamel suited to grinding, may have left it with less flexibility when the menu changed. It was not simply weaker or less intelligent than its Homo contemporaries. It was simply more specialised, and in evolutionary roulette, specialisation is sometimes a losing bet. Alongside Paranthropus were other Homo forms, though their classification is debated. At sites like Dmanisi in Georgia, fossils around 1.8 million years old reveal a remarkable diversity within what is often called Homo erectus. Some skulls are large-brained, others smaller, some with projecting faces and others flatter. This variation raises the question, were these all one species or several lineages trying parallel solutions to the same challenges? By the time we reach 1,000,000 years ago in Africa, fossils like KNMER, 42,700 from Kenya, or cranial pieces from Buea in Eritrea show that diversity persisted. Yet not all those variants left descendants. Many seem to vanish. their populations perhaps too small or too isolated to endure the climatic swings of the mid-Pleistocene transition. The information from places like Atapuerca in Spain adds another dimension. At the Grandolina site, fossils dated to about 800,000 years ago reveal a population with both primitive and derived features, classified by some as Homo antecessor. Whether it was a direct ancestor to later Europeans or simply another branch cut short is debated. What matters is that the human family tree was not a neat trunk but a tangle. Homo erectus in Asia, Homo ergaster in Africa, and forms like Homo antecessor in Europe all overlapped in time. Some adapted to local conditions, others faded. The disappearance of these populations reminds us that evolution is not about progress but persistence. One haunting example comes from South Africa. Fossils attributed to Homo erectus are found there, but so too are enigmatic remains that resist neat classification. The cave systems preserve teeth and fragments that show combinations of traits, some more primitive, some more advanced. It may be that southern Africa harboured small, regionally distinct populations that never expanded widely. Their stories are lost not because they were unimportant, but because their traces were too fragile to endure. The resolution of this chapter is sobering. Homo erectus endured because it combined mobility, technological adaptability and dietary breadth. Its handaxes could process meat, wood and plant matter. Its groups could range across grasslands, forests and coasts. Its populations were large enough and spread widely enough to buffer against local extinctions. In contrast, Paranthropus depended on habitats that contracted, and smaller Homo variants may have lacked the numbers to withstand competition or climate stress. This does not mean Homo erectus was superior in a moral or cultural sense. It simply happened to be better buffered against change. The haunting question remains: what would our world look like if Paranthropus had endured, grinding sedges beside riverbanks while our ancestors chipped stone? Or if Homo antecessor had flourished, shaping a different path of humanity in Europe? Evolution left us as the inheritors, but the silence of those who did not survive is part of our story too. If we linger on the question of those who did not survive, the picture becomes even more complicated when we leave Africa and look outward. Around 1 million years ago, populations of Homo erectus were already well established in parts of Asia. From the caves of Zhoukoudian near Beijing to sites in Indonesia, such as Sanggaran. Yet, scattered among these larger stories are traces of other hominins whose identities remain ambiguous. In the Caucasus, at Dmanisi, the fossils remind us of just how variable these early humans were. Some skulls are small and gracile, others robust and broad. Jaw size, brain volume, and facial form differ enough that, if found in isolation, they might once have been assigned to entirely separate species. The fact that they come from one location and one time forces us to reconsider what species even means when applied to our genus during this period. Were these differences evidence of sexual dimorphism, regional adaptation, or simply the natural variation within a single population? Or was there more diversity present, with small local lineages arising and vanishing before they could leave much of a fossil trace? In India and Southeast Asia too, stone tools appear at dates close to 1.5 million years ago, yet fossils are scarce. Some scholars wonder whether populations of early Homo beyond Africa sometimes represented dispersals that failed, thinly spread groups that could not maintain themselves when climates turned unstable. These ghost populations may never be identified by bone, but their presence is hinted at by tools, flakes, and cores lying mute in river terraces. In some sense, they are competitors too, not because they were distinct species, but because they represent human lives that did not feed back into the later story of survival. Another layer of competition came not from hominins but from the larger mammal community. It is worth remembering that the early Pleistocene landscape was not a stage waiting for humans to dominate, but a crowded field of grazers, browsers, and predators. When Homo erectus scavenged elephant carcasses, they did so in rivalry with hyenas and saber-toothed cats. When Paranthropus bent to uproot sedges, they shared the patch with giant baboons of the genus Therapithecus. The evolutionary test was not simply hominin versus hominin, but hominin against the entire ecology of East Africa. Some lineages of Homo may have been as vulnerable to these pressures as Paranthropus was, their populations unable to expand because competitors, animal or human, closed the door on their niche. The disappearance of these groups also raises questions about demography. Small groups, no matter how skilled or well adapted, face higher risks of inbreeding, disease outbreaks, or local catastrophe. A volcanic eruption or prolonged drought could erase a community too small to recover. In contrast, Homo erectus spread so widely that local disasters could be absorbed into a larger network of populations. That redundancy may have been decisive. When we ask why some survived while others vanished, numbers matter as much as anatomy. We should also consider the possibility that extinction was not always dramatic. For Paranthropus, the decline may have been slow, stretched across tens of thousands of years. Populations dwindled, ranges contracted, and eventually there were too few left to leave fossils. For smaller Homo lineages, the end might have been quieter still, not a catastrophic die-off but a gradual absorption. Groups may have interbred with more numerous Homo erectus populations, their distinctive traits diluted until they disappeared into the wider gene pool. If this happened, the competitors we imagine may not have been entirely lost, but survive in faint echoes within us, their contribution folded invisibly into the lineage that continued. The haunting question that lingers is not only why they failed, but what was lost with them. Did Paranthropus have behaviours, calls, or social patterns that were unique, never replicated in Homo? Did smaller Homo lineages possess ways of living or adapting that might have offered different futures had they persisted? When we reconstruct prehistory, we often focus on winners, the lineages that led to us. Yet the evolutionary experiment was broader. At 1 million years ago, the world held multiple solutions to the problem of being a bipedal primate in a volatile climate. The fact that only one path survived should not blind us to the richness of what was tried and lost along the way. In that sense, the competitors are not just vanished species, they are reminders of how fragile survival is, and how much of our evolutionary history is written in absence as much as presence. We live in the aftermath of extinctions, carrying forward the legacy not just of those who endured but also of those who did not. Their silence shapes the story we tell because it defines the narrowing of possibilities that eventually produced us. If you could arrive in East Africa 1 million years ago, the first thing to strike you would not be a hominin, but the vastness of the landscape. The rift valleys open like scars across the continent. Their escarpments broken by freshwater lakes that rose and fell with the rhythms of climate. Some basins shimmered with water under the glare of the sun, others lay cracked and empty, leaving alkaline flats that smelled faintly of minerals and decay. Around the lakes, belts of gallery forest formed green fringes that rustled with bird calls and the buzzing of insects. Beyond these, grasslands stretched, dotted with acacia and euphorbia, carrying the scent of dust, dung, and the faint sweetness of flowering shrubs. You would hear the calls of antelope herds long before you saw them. Alcelephines, gazelles, and giant buffalo grazed in restless clusters. Elephants moved slowly across the plain, their tusks long and curved, their massive feet pressing deep into the soil. Among them might be seen the straight-tusked relatives of today's elephants, animals taller than any modern counterpart. Hippos churned the shallows of the rivers, surfacing with blasts of sound that echoed through the evening air. Crocodiles lurked along the edges, their movements almost imperceptible until they struck. It was not just the megafauna that filled the scene. The grass itself carried signals of the shifting world. Stable isotope analyses show that C4 grasses dominated these habitats, resilient in the face of fluctuating rainfall. Yet in places, woody cover encroached, patches of scrub and bushland interrupting the openness. This mosaic made the world unpredictable. A predator could hide behind a thicket where yesterday there had been none. For grazers, the shifting balance between open plain and shaded cover meant constant movement, tracking the greenest patches across kilometres of terrain. Paranthropus boisei still walked here, though faintly, like an echo about to vanish. Their heavy jaws and sagittal crests marked them out, but in life they would not have seemed grotesque. They were squat, robust hominins, likely foraging in groups, plucking sedges from wetlands or pulling tubers from softer soils near water. If you watched them from a distance, you might see the repetitive labour of chewing, a daily ritual as necessary as it was unrelenting. The sound of grinding plant matter, the rhythm of jaws, was the soundtrack of their survival. Yet these patches of grass and sedge were shrinking, contested not just by antelope but by giant baboons that shared their diet. Each year made it harder for these specialists to persist. Not far away, a different figure was shaping stone. Homo erectus, taller and longer-limbed, crouched beside a scatter of flakes. The percussion of stone on stone rang sharply, echoing off canyon walls. Handaxes, crude yet purposeful, emerged from the core. These tools were not made for grass or tubers, but for carcasses. The smell of meat lingered where bones lay split, marrow leaking in sticky residue. Vultures circled overhead, their shadows passing quickly across the ground. Lions and hyenas approached, waiting their turn, but the stone edge meant humans often got there first. To stand at this moment was to witness a subtle shift in power, one that would ripple outward for the next 1,000,000 years. The air itself told part of the story. Carbon dioxide levels had climbed from earlier lows, altering vegetation in ways that reshaped the menu of both herbivore and hominin. Clouds rolled across the highlands, dropping rains that could be generous one year and stingy the next. With the shifting of the mid-Pleistocene transition, glacial cycles lengthened, dragging ecosystems along with them. For the beings who lived in this world, stability was an illusion. To survive was to adapt, to keep moving, to know when to risk and when to retreat. The predators kept the tension sharp. Saber-toothed cats still prowled, their elongated canines flashing as they tore through the hide of zebra. Hyenas worked in packs, crunching bone with the efficiency of living crushers. Leopards carried kills into trees, leaving bones to drop among branches. To hear the night in this world was to hear fear itself. The cough of a lion, the laugh of hyenas, the scream of prey cut short. For hominins huddled together, whether in shallow shelters or beneath skins, the dark was never quiet. And yet there was also cooperation. Footprints frozen in mud at sites like Illyric showlines of early humans walking side by side, their gait steady and human-like. They were not solitary wanderers, but groups, travelling with children, carrying knowledge of where the water lay. These tracks are among the few moments where we glimpse life as it was lived, not just as fossils in rock. So what would it feel like to stand at this turning point? You would see two humankinds sharing a world, one narrowing into extinction, the other stretching outward with tools and growing brains. You would see ecosystems dense with life, herds churning dust, rivers swelling with hippos, skies raked by vultures. You would feel the instability of a climate that refused to settle. Above all, you would sense impermanence. Every footprint, every cracked bone, every withered stalk of grass whispered the same truth. That survival was provisional, that nothing was guaranteed, and that even here, in this world of abundance and danger, the future was already being written in the stones and in the choices of those who wielded them. And if you let yourself listen closely, you might ask the same question as scientists ask today. Was this world so vivid and precarious, more alien to us, or more familiar than we would like to admit? When we imagine survival 1,000,000 years ago, it is tempting to picture a straight ladder, with one species neatly handing over the torch to the next. But what the fossil record actually shows is a branching bush where many lineages coexisted, sometimes for hundreds of thousands of years, before some simply slipped away. The ground at sites like Cuviphora, Olduvai, and Dromolen reminds us that the story of humanity was never guaranteed. It was a competition of endurance, of who could outlast shifts in rainfall, who could stretch their diet across a changing menu, and who could rear their young long enough to reproduce before disaster struck. Among these competitors were forms of Homo that do not quite fit cleanly into categories. At Dmanisi in Georgia, skulls just under 2 million years old suggest astonishing variation within a single group. One cranium is large and elongated, another small and rounded, yet they may all belong to what we call Homo erectus. That variability forces us to wonder, were some of these early Homo populations separate species, or just flexible versions of the same? Whatever the answer, some of these lineages did not persist past the 1,000,000-year mark. Their bones are there, but their stories end abruptly. Even within Africa, there are hints of populations that seem close to us, but are no longer present. The finds at sites such as Buya in Eritrea or Buri in Ethiopia reveal hominins with mosaics of features, neither fully erectus nor yet fully something else. They are the evolutionary cousins who walked alongside our ancestors for a time, their presence a reminder that diversity was the rule, not the exception. Their disappearance is not fully explained, but the lesson is clear. Survival was never about perfection, only persistence. Looking back at this crowded stage, what stands out is not just the fact that Homo erectus survived, but that it did so while other promising experiments in humanity did not. That difference could have been diet, or cooperation, or simply luck across generations of harsh seasons. It leaves us with a haunting thought. Our species descends from survivors not because they were destined to prevail, but because they happened to be in the right ecological window when others fell away. The bones of those who almost made it are silent now, but their presence still whispers the fragility of existence. Why them, not us? It is the simplest question to ask at the close of a million-year story, and the most difficult to answer without slipping into myth. Standing in the fossil record at the 1 million year mark, we can see clearly that we were not alone. There were other hominins walking upright, chewing roots, striking stone and raising young. Paranthropus was still gnawing on grasses. Early branches of Homo were still scattered across Africa and Eurasia. Even in places we least expect, such as the far islands of Southeast Asia, experiments in humanity were already underway. Yet when the dust settled, only one lineage would eventually continue the story that leads to us. That contingency, the sheer chance that our ancestors were the ones who survived, is the haunting question that shadows every fossil dig. The extinction of Paranthropus is perhaps the clearest reminder that even robust design cannot guarantee survival. Their skulls seemed built for endurance, with massive jaws and ridges for chewing muscles. They looked immovable, as though nothing could dislodge them from the African grasslands, yet they vanished. Climate instability, shrinking habitats, competition with both grazing animals and more flexible hominins, any combination of these could have been the trigger. We cannot point to a single event, no dramatic catastrophe, only the slow erosion of opportunity. They did not fail in a dramatic battle with our ancestors. They faded away as the landscape shifted beneath their feet. That is the uncomfortable truth. Being well adapted to yesterday's world does not promise survival in tomorrow's. The same is true for the other Homo variants. In places like Dmanisi, we see evidence of remarkable adaptability. Small-bodied people moving into Eurasia with stone flakes and courage. Yet those particular populations left no descendants we can trace. In East Africa, we see hominins with faces not quite Erectus and not quite anything else. They too disappear from the record. Their bones tell us they once thrived, but they do not tell us why they stopped. In all likelihood, extinction was not the result of weakness, but of circumstance. A drought lasting a little longer than expected, a population failing to recover after disease, or a predator taking too many of the young. That recognition, that survival often depends on contingency rather than superiority, is hard for us to accept. Our storytelling instincts want victors and losers, a narrative in which Homo succeeded because it was destined to. Yet science does not support such neat arcs. The fossil record shows overlapping species, long coexistence, and abrupt vanishings. If Homo erectus had disappeared 1 million years ago and Paranthropus had somehow endured, perhaps another version of intelligence might have emerged, chewing seeds in the forest margins, solving problems with different tools. We do not know, because that world never came to be. What we have instead is a silence filled with bones. There is also the problem of bias. Fossils only preserve under narrow conditions, and chance determines what survives for us to study. Entire populations may have flourished and vanished without leaving a trace we can recognize. When we compare Homo erectus with Paranthropus, we are comparing fragments of a vast and incomplete picture. It is possible that some branches of Homo endured through sheer luck of geography, living in areas buffered from the worst of climate swings, while Paranthropus happened to occupy the ecological margins most prone to collapse. In evolutionary terms, luck is not trivial. It shapes who persists long enough to become an ancestor. This is why humility is essential in telling deep time stories. We cannot claim that Homo was smarter, braver, or destined for greatness. We can only say that it survived the particular challenges of the time while others did not. That is a subtle but profound difference. It reframes our presence today not as a triumph of superiority, but as the outcome of survival in a shifting game of chance. The haunting question is not why they failed, but why we were spared. When we picture Paranthropus disappearing from East Africa, we're also picturing the loss of an entire perspective on the world. These were not failed humans, they were successful hominins for over 1 million years, far longer than many species ever persist. Their extinction does not erase their achievement. If anything, it reminds us that even long success can end abruptly. Their disappearance echoes the broader law of evolution. 99% of all species that ever lived are gone. Extinction is the rule, survival the rare exception. We are standing in that rare exception, and that precariousness is what makes the fossil record so haunting. Consider also the scale of coexistence. For hundreds of thousands of years, multiple hominins shared landscapes. That fact alone challenges any sense of inevitability. If you were alive 1 million years ago, you could not have predicted which lineage would dominate the future. Looking at a valley with Paranthropus gnawing tubers on one side and Homo erectus chipping stone on the other, the outcome would have been impossible to foresee. Both looked viable. Both had been viable for a very long time. The haunting truth is that one of them was only a few evolutionary steps away from permanent disappearance. There is an existential lesson in this. We often think of evolution as progress, a march toward us. But in reality, it is a branching process with no final destination. The fact that we are here does not mean evolution aimed at us. It means that of all the possible outcomes, this is the one that happened. Had the climate shifted differently, or had disease struck our ancestors more severely, or had one volcanic eruption covered the wrong valley, the story might have ended without us. The haunting question is not why Paranthropus is gone, but why humanity, against the odds, remains. The question lingers in part because extinction leaves silence. A tool, a tooth, a fragment of jaw can tell us about diet and movement, but it cannot tell us what it felt like to be Paranthropus watching the forest encroach on the grassland, or Homo erectus watching the rivers dry. We can reconstruct isotopes, pollen and footprints, but we cannot know what decisions they made each day, what they feared, or whether they sensed their numbers thinning. The silence of their perspective forces us to admit how much is lost forever. That absence is what makes their disappearance so haunting. For us, reflecting on 1 million years ago is not only about cataloguing fossils, but about understanding fragility. The hominins who did not survive remind us that we too are temporary. Our species is younger than the lifespan of Paranthropus. If they thrived for over 1 million years and still vanished, we cannot assume permanence. In that sense, the haunting question is not just why them, not us, but also when us. How long before our own branch faces the same silence? And so the closing reflection is this. We do not know why we survived when others did not. The evidence we have suggests contingency, adaptation, and chance. We should resist the temptation to tell it as a victory story. Instead, it is a reminder of vulnerability, a call to humility, and perhaps even a comfort. We are part of a much larger pattern where survival is always provisional. That pattern ties us not only to the ancestors who lived 1 million years ago, but also to the countless species who never reached this present moment. In the quiet of that realization, the haunting question lingers, unanswered as it should. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.